The next era of nations may be decided by rail. Across mountains and borders, the world's most ambitious railway megaprojects are being built to reshape economies and connect places once thought unreachable. Today, we follow the hyperlinks transforming the map and uncover the engineering battles and hidden challenges behind the race to build the future on steel. Hidden behind its historic Beaux-Arts facade, Chicago Union Station is undergoing a long-term transformation that positions it among the city's most complex and consequential megaprojects. Rather than a single construction effort, the Union Station redevelopment is a layered program of renovations, expansions, and adjacent real estate projects designed to modernize a century-old transportation hub while it continues to serve hundreds of thousands of daily passengers. Union Station originally opened in 1925 and was designed for an era when long-distance rail travel dominated intercity transportation. Over time, train volumes declined while commuter traffic surged, leaving the station undersized for peak demand and outdated in its circulation, safety systems, and passenger amenities. By the early 21st century, deferred maintenance and congestion had become systemic problems, prompting a phased redevelopment strategy rather than a full shutdown reconstruction. Early modernization work began in the 2010s with targeted interior renovations. These included structural repairs, roof restoration, upgraded electrical and mechanical systems, and improvements to life safety infrastructure. The iconic Great Hall underwent a major restoration completed in the late 2010s, addressing water infiltration, damaged stonework, and aging lighting systems while preserving historic architectural elements. A key milestone in the redevelopment timeline was the reopening of the Chicago River entrance on the station's west side. This new access point, completed in the early 2020s, created a direct pedestrian connection between Union Station and the Riverwalk. Construction required excavation, floodproofing, and the installation of new vertical circulation systems, all while maintaining rail operations below. Passenger circulation improvements have been central to the project. New corridors, widened passageways, and reconfigured waiting areas have been built incrementally to reduce bottlenecks during rush hours. These changes are designed to accommodate future ridership growth driven by increased metro service and potential intercity rail expansion. Beyond the station itself, the redevelopment includes major overbuild and adjacent construction projects that rely on Union Station's air rights. The most prominent is the Union Station Tower development on the south side of the station. Construction of this high-rise office tower began in the early 2020s and required building directly over active rail tracks. This involved the installation of massive transfer girders, vibration isolation systems, and precisely sequenced foundation work to avoid disrupting train service. Additional overbuild phases are planned for the north side of the station, with long-term proposals envisioning multiple towers constructed above rail infrastructure. These future phases remain dependent on market demand and financing, but are entitled under the broader redevelopment framework. If fully built out, the overbuild components would add millions of square feet of office and mixed-use space above one of the busiest rail terminals in the country. Transit infrastructure upgrades are another major element. Platforms and track-level systems have been incrementally improved, including drainage upgrades, platform edge repairs, and signal coordination work. These projects are often executed overnight or during limited service windows, extending timelines but allowing continuous operation. From a construction sequencing perspective, Union Station's redevelopment is uniquely constrained. All work must be phased around active Amtrak and Metra service, limiting the size of work zones and requiring extensive temporary supports. This has stretched what might otherwise be a decade-long rebuild into a multi-decade mega-project. In 2026, several major extensions of the Bay Area rapid transit system are under construction, forming a critical part of Northern California's long-term transit infrastructure strategy. The largest and most technically complex is the Silicon Valley Phase 2 extension, a 6-mile expansion of BART service from Berryessa, North San Jose, to downtown San Jose and Santa Clara. This project is being led by the Santa Clara Valley Transportation Authority in partnership with BART and is a federally funded, multi-billion-dollar endeavor. Construction in 2026 is fully active along the entire Phase 2 alignment. The project includes 4 new stations: 28th Street, Little Portugal, downtown San Jose, Diridon, and Santa Clara. Approximately 5 miles of the alignment will be constructed using a single-bore tunnel, 45 feet in diameter, making it one of the largest subway tunnel sections in North America. In 2026, tunneling operations are scheduled to begin following completion of launch shaft excavation and assembly of the tunnel boring machine. Shaft construction and staging zones are already established at multiple sites, including the western portal near Diridon Station. The downtown San Jose station, which will be built underground, presents specific challenges due to its depth and proximity to active utilities, heritage buildings, and seismic zones. In 2026, deep excavation, support of excavation walls, and early concrete pours are underway. Similar substructure work is progressing at 28th Street and Diridon, where retained cut and mined station boxes are being constructed. Cut and cover methods are being used at the Santa Clara station, which will serve as the new western terminus of the extension and will include a surface-level tail track and storage tracks. The entire Phase 2 extension is projected to open for revenue service by 2036, with major civil work and tunneling expected to conclude by the early 2030s. The project's integration with existing transit hubs, including Caltrain, Amtrak, VTA Light Rail, and future California High-Speed Rail at Diridon, is a key element of the design. In 2026, intermodal design coordination is ongoing between BART, VTA, Caltrain, and city agencies to synchronize platforms, vertical circulation, and fare systems. Elsewhere in the Bay Area, BART is continuing with other network improvement projects in 2026. This includes planning and pre-construction for the potential extension to Livermore along the I-580 corridor. Although not yet in full construction, right-of-way acquisition and environmental reviews are active. This corridor is intended to close a critical gap between Dublin, Pleasanton, and the Tri-Valley region. Throughout Central and Southern California in 2026, university campuses are undergoing large-scale construction to accommodate rising enrollment, research expansion, and updated sustainability mandates. These developments span multiple University of California and California State University institutions, with a focus on housing, laboratories, medical infrastructure, and renewable energy integration. At the University of California, Merced, construction continues on multiple academic and housing facilities under the 2020 Project Phase 2, expanding the campus's capacity well beyond its original footprint. In 2026, vertical construction is active on new science and engineering buildings, along with residential halls that will add over 1,000 new beds by 2027. These additions support UC Merced's long-term goal to serve over 15,000 students and enhance its research output in agricultural technology and climate science. In 2026, construction begins in earnest on the Los Angeles Metro Southeast Gateway Line, a major light rail expansion aimed at delivering high-capacity transit service to some of the most densely populated and historically underserved communities in southeast Los Angeles County. Previously known as the West Santa Ana Branch Transit Corridor, this project represents one of the largest new rail corridors in the region and forms a critical part of the county's long-term Measure M mobility strategy. The project's first operational phase will span 14.5 miles, linking the existing A-Line station at Slauson in South Los Angeles to a new terminal station at Pioneer Boulevard in Artesia. This segment will include 9 new stations and is designed to serve communities across Huntington Park, Bell, Cudahy, Southgate, Downey, Paramount, Bellflower, and Artesia. As of 2026, the corridor is in the early stages of pre-construction and enabling works, with heavy utility, relocation, environmental mitigation, and corridor preparation now underway. Utility relocation is a primary focus in 2026. In multiple cities along the alignment, electrical, gas, water, and telecommunications lines are being moved to accommodate future construction of the light rail guideway and associated infrastructure. In Artesia, crews are also performing grading work and beginning access improvements in preparation for major station excavation and track installation, which is expected to ramp up in 2027. The project is being delivered under a progressive design-build model. A joint venture of Flatiron, Dragados USA, and Herzog is leading the initial pre-construction phase under a contract valued at over $997 million. This early work includes soil testing, demolition of outdated facilities, geotechnical surveys, and engineering refinements along the right-of-way. These preparatory efforts are critical to mitigating delays once full construction begins. The total cost? For the Southeast Gateway Line, Phase 1 is projected at approximately $8.6 billion. The project is being funded through a combination of local sales tax measures, including Measures R and M, along with state transportation funds and a significant request for federal support through the FTA's New Starts Capital Investment Program. Metro is targeting a full funding grant agreement from the federal government by 2027. The alignment follows a former Pacific Electric Railway corridor with portions of the route adjacent to active freight lines. In 2026, Metro and its construction partners are actively coordinating with freight rail operators to ensure clearances, right-of-way agreements, and safety systems are in place. Quiet zones, grade separation structures, and fencing are being designed, and in some areas, early site work has begun. The line will use low-floor light rail vehicles, similar to those operating on Metro's existing lines, with stations designed for full ADA accessibility. Platforms, traction power substations, and signal control infrastructure are all in the design phase in 2026, with final engineering packages expected to be released for construction bidding in 2027. The Pacheco Pass segment falls within the broader Merced to San Jose section, which is in the advanced pre-construction phase. Full-scale construction is expected to begin in late 2026 or early 2027, following the completion of design, environmental permitting, and contractor procurement. In 2026, geotechnical investigations are being conducted at multiple points across the alignment, including test drilling to analyze subsurface conditions, fault mapping near the Calaveras and San Andreas fault zones, and seismic risk assessments required for final tunnel engineering. The tunnel alignment will require 2 main bores with an internal diameter of approximately 40 feet each, separated by cross passages every 1,000 to 1,500 feet to allow emergency access and pressure equalization. An intermediate access shaft is also planned in the vicinity of Casa de Fruta to provide tunnel boring machine launch capability and logistical support during construction. The geology of the Diablo Range presents significant challenges with faulted rock zones, variable water inflows, and compressible soils in valley transitions. Tunneling will be conducted using pressurized tunnel boring machines capable of navigating mixed face and high pressure conditions. The Pacheco Pass tunnels will pass under critical infrastructure, protected habitat areas, and seismic fault lines, requiring advanced lining systems and continuous monitoring. Designs include seismic isolation joints and drainage galleries to mitigate fault displacement risk and groundwater intrusion. Tunnel depth will range from 100 to over 1,000 feet below surface, depending on terrain. Ventilation and safety systems, including emergency egress, fire protection, and pressurization controls, are part of the ongoing systems design effort in 2026. Upon completion, the tunnels will enable a seamless high-speed rail corridor from Merced to Gilroy, reducing rail travel time across the pass from over an hour to just under 15 minutes. Combined with viaducts, embankments, and cut and fill, sections across the San Joaquin Valley and into the Santa Clara Valley, the Pacheco Pass alignment represents one of the most capital-intensive and engineering-heavy components of the entire HSR system. The full Merced to San Jose segment is targeted for phased operational readiness beginning in the early 2030s, contingent on funding and right-of-way clearance. In 2026, contract packaging and procurement strategy are being finalized. The tunnel construction will likely be delivered as part of a design-build package, integrating civil structures, systems, and tunnel fit-out under a single delivery framework. Coordination with Caltrain and Union Pacific Railroad in the Gilroy area is also active in 2026, where blended operations with existing rail infrastructure are being planned. At full build-out, the Pacheco Pass tunnels will serve as the gateway between the Central Valley's agricultural and inland urban centers and the tech-driven economy of Northern California. The tunnels are expected to handle multiple high-speed rail trains per hour in each direction, forming a high-capacity backbone for statewide intercity travel. Their construction, once launched, will take an estimated 6 to 7 years, involving around-the-clock excavation and a continuous logistics chain to manage spoil removal, liner segment installation, and tunnel utility integration. The Los Angeles Metro D Line Extension, formerly known as the Purple Line Extension, is a $9.3 billion mega project that is carving through some of the busiest, most congested corridors in California. This 9-mile westward expansion of heavy rail is unfolding in 3 carefully staged phases, each one bringing new connectivity to the city's west side. Construction began in 2014, and as of 2026, 2 of the 3 segments are deep in advanced construction, while the third is fully underway. The first section, stretching 3.92 miles from Wilshire Weston to Wilshire La Cienega, was scheduled for completion in 2025. Tunneling for this segment was completed in 2021, with station construction and systems installation now in final phases. Crews are outfitting stations with electrical, ventilation, and communication systems, while surface-level integration work continues at key intersections. The second segment, running from Wilshire, La Cienega to Century City, adds another 2.59 miles of dual-bore tunnel. This phase includes the construction of 2 stations, Wilshire Rodeo in Beverly Hills and Century City Constellation. By 2026, excavation is complete and station interiors are progressing, with structural, mechanical, and architectural elements being finalized. This portion of the line is projected to be operational in 2026. The final segment, extending 2.56 miles to the VA hospital in Westwood, is scheduled for completion in 2027. Tunneling began in 2021, with both tunnel boring machines reaching the Westwood UCLA station box by mid-2024. By 2026, structural work at both Westwood stations is active, including excavation, waterproofing, and concrete shell construction. This third phase is particularly complex, not only due to proximity to critical federal and medical infrastructure, but also because of seismic design considerations near the Santa Monica Fault. All 3 phases are being constructed simultaneously to streamline delivery, maximize cost efficiency, and align operational readiness. Together, they form a continuous underground transit spine linking downtown Los Angeles to Beverly Hills, Century City, and Westwood, some of the region's highest density employment and residential zones. When complete, the D-Line extension will connect riders to major institutions including UCLA, Cedars-Sinai Medical Center, and a cluster of Fortune 500 offices in Century City. By the time the full extension opens in 2027, the D-Line will operate across 13 miles from Union Station to the VA hospital in Westwood, serving nearly 80,000 weekday riders. This will dramatically reduce commute times along the corridor, potentially cutting rush hour trips from over an hour by car to under 30 minutes by rail. In addition to relieving pressure on the 10 and 405 freeways, the D-Line will improve access to key transit interchanges, including connections with the B-Line, E-Line, and multiple local and express bus routes. In 2026, deep excavation work is underway in the heart of California's rugged Diablo Range. At the core of this activity lies the Pacheco Pass tunnels, two parallel bores that will become the most technically demanding segment of the state's high-speed rail system. Spanning approximately 13.5 miles between the Central Valley and the Santa Clara Valley, this tunnel system is being designed to support trains traveling at speeds up to 220 miles per hour. Once complete, it will form the primary mountain crossing linking the Silicon Valley to the rest of the California high-speed rail network. By 2026, Brightline West has shifted from a proposal into a full-scale Nevada megaproject defined by earth-moving, structures, and systems planning along the I-15 corridor. The project is designed to create a dedicated high-speed rail link between Las Vegas and Southern California, using grade-separated passenger rail infrastructure built for sustained high speeds and frequent service. Construction activity visible in Nevada in 2026 is concentrated around the Las Vegas Valley approach and the corridor's major structure zones. Crews are advancing right-of-way preparation, clearing and grading embankments, and building the subgrade that will carry ballastless track or slab track segments in the highest speed areas. Where the alignment crosses local roads and drainage corridors, 2026 work includes bridge abutments, pier foundations, and precast girder placement to keep the rail line fully separated from traffic. Station development is another major 2026 focus. The Las Vegas terminal site is being prepared with deep utility relocations, foundation work, and early vertical framing for passenger areas and platform structures. This phase also includes the less visible but critical backbone systems, traction power planning, feeder routes, and spaces for substations that will convert and distribute electricity along the line. As these power sites are finalized, contractors install duct banks, conduit runs, and equipment pads that must be in place before rail systems can be energized. Rail systems work ramps up through 2026 in parallel with civil construction. Signal and communications contractors are installing cable routes, equipment rooms, and mounting points for wayside hardware. Because high-speed operations rely on precise train control, this stage is about building the physical network that will later support automated protection, dispatching, and continuous monitoring. Along windy desert segments, teams also implement sand and drainage mitigation, including channel improvements, erosion control, and protective barriers that reduce the risk of drift material accumulating near the track. A defining feature of 2026 construction is sequencing around access and safety. Much of the alignment runs within or adjacent to freeway right-of-way, so the work plan is built around traffic management, night closures, and stage construction zones. Heavy haul deliveries, concrete pours, and crane picks are scheduled to minimize disruption while maintaining steady progress on structures and guideway elements. Timeline-wise, Brightline West has been framed as a late 2020s delivery, with the most frequently discussed target being service in 2028, assuming civil works, systems integration, and testing proceed without major delays. For a project of this type, 2026 is the year that locks in the schedule. If the alignment's major structures, station shells, and power readiness milestones stay on track, 2027 becomes the transition into full track installation, electrification, and corridor-wide testing. By 2026, the Brightline Miami to Orlando corridor is less about building a brand new railway and more about expanding the capacity and reliability of an intercity system that now has to perform like daily infrastructure. In the Miami megaproject context, the construction story in 2026 is a mix of corridor hardening, speed and schedule improvements, and station area build-outs that let the service handle higher ridership without degrading on-time performance. A major 2026 workstream is right-of-way and track capacity. Crews focus on additional double tracking in remaining single-track segments, plus new crossovers and turnouts that allow trains to pass and recover from delays. That work includes ballast and subgrade, improvements, replacement of rail fasteners and ties in high-wear zones, and drainage upgrades where South Florida rain events can saturate track beds and reduce stability. Bridge approaches and elevated sections receive structural inspections and targeted reinforcement so the line can maintain consistent speeds without imposing seasonal slow orders. Grade crossings remain a defining constraint for any Florida passenger line that runs at higher speeds. In 2026, construction activity typically concentrates on upgrading crossing surfaces, installing improved warning systems, and adding intrusion detection where feasible. Roadway tie-ins and traffic signal coordination near crossings are part of the same package, because the goal is not only safety, but fewer unplanned slowdowns caused by vehicle conflicts and queue spillback. Systems work expands in parallel. In 2026, signal and communications upgrades are key, including new equipment huts, fiber runs, and power conditioning systems that stabilize train control and dispatching. Where higher frequencies are planned, the corridor needs tighter block spacing and more resilient redundancy, so crews are installing and testing additional wayside hardware and networked monitoring equipment that feeds centralized operations. Stations and terminal interfaces also drive construction in 2026, especially around Miami Central and the Orlando Airport Terminal, where passenger volumes create pressure on circulation space. Work in this phase tends to include platform and canopy improvements, expanded vertical circulation, and upgraded passenger processing areas such as queuing, ticketing, and security adjacent zones. Back-of-house systems are upgraded too, including maintenance access, cleaning and servicing areas, and power distribution that supports more frequent departures. A less visible but critical 2026 construction program is resilience. Coastal South Florida infrastructure has to account for flooding, salt corrosion, and extreme heat. That pushes investment into corrosion protection, electrical room hardening, improved pumping, and drainage at low points, and redundant communications pathways so service can be restored quickly after severe weather. Across the Northeast Corridor, the Gateway program's Hudson River Tunnel component is one of the most consequential transportation megaprojects in the United States. But in a 2026 focused video, it should be framed as a project reaching critical construction acceleration rather than full end-of-project completion. Its purpose is to build new passenger rail tunnels under the Hudson River between New Jersey and Manhattan, and then allow the existing century-old tunnels, which were heavily damaged by saltwater intrusion during Hurricane Sandy, to be rehabilitated without cutting the region's rail capacity in half. That is why the project is treated as a national infrastructure priority rather than a local rail upgrade. The core problem is capacity and reliability. The existing two-track tunnel is a bottleneck for intercity and commuter rail traffic entering Penn Station. It carries Amtrak and NJ Transit trains on the busiest passenger rail segment in the country, yet it lacks redundancy. Any major service disruption affects travel across the Northeast. The new tunnel project is intended to solve that by adding parallel tunnel capacity first, creating the conditions for later rehabilitation of the old tubes while maintaining service. The important point is that 2026 is associated with major active construction and package-level milestones, not with the final opening of the full tunnel system to passengers. In that year, the key work is expected to include continued heavy civil construction on approach structures, tunnel portal, areas, retaining structures, utility relocation, ground improvement, excavation support, concrete works, and early tunnel-related infrastructure on both sides of the river. Where contracts are advanced enough, 2026 activity also includes site preparation for full tunneling operations, staging areas, access shafts, and the supporting infrastructure needed before boring or immersed structural progress can translate into final rail systems installation. The project is unusually complex because it is not only a tunnel beneath a major river. It has to connect into one of the most constrained rail environments in North America. On the Manhattan side, work must interface with Penn Station approaches, densely developed urban blocks, utilities, transportation corridors, and existing rail operations. On the New Jersey side, the alignment must tie into the broader network while managing wetlands, embankments, and active right-of-way conditions. Every phase depends on sequencing, civil, structures, ventilation and safety provisions, drainage, trackbed preparation, and future system spaces all have to be coordinated long before trains can operate. Another major issue for the 2026 timeline is that the Gateway program is not a single construction contract. It is a portfolio of interdependent elements, including tunnels, portal works, bridge-related interfaces, and supporting rail infrastructure. Because of that, completion can mean different things depending on the contract package being discussed. Some enabling components may reach major completion earlier, but the overall Hudson River Tunnel element remains part of a longer delivery schedule extending beyond 2026. Beneath some of the most congested streets in Los Angeles, the LA Metro D-Line extension, Section 1, is the underground transit project intended to deliver one of the city's most important rail expansions of the mid-2020s. For a video about United States megaprojects completing in 2026, this segment matters because it represents the final stage of transforming years of tunneling and station construction into an operating subway link. Section 1 extends the D-Line west from its former terminus at Wilshire/Weston to new stations at Wilshire/La Brea, Wilshire/Fairfax, and Wilshire/La Cienega. This first section is the opening piece of a much larger corridor expansion designed to push heavy rail farther through the Wilshire Corridor, one of the densest employment and destination corridors in Southern California. Its value is not only in adding track mileage, it creates new direct subway access to major cultural, commercial, and residential districts while reducing dependence on slow surface traffic along Wilshire Boulevard. That makes Section 1 a foundational part of a broader network change rather than a standalone line. The most significant construction already involved tunnel boring, cross passages, station excavation, concrete structural work, and the build-out of underground platforms and circulation areas. By the final approach to completion, the work shifts away from excavation and toward railway systems and passenger facilities. In a 2026 completion context, the critical construction activities are the finishing of station interiors, installation and testing of elevators and escalators, completion of ventilation and fire life safety systems, traction power energization, track and third rail finishing, signal integration, communication systems, fare equipment, and the final architectural treatment of entrances and public-facing spaces. Another major task in the completion phase is systems commissioning. For a subway extension, the project is not complete when the tunnels and stations are physically built. Metro and contractors must test train control systems, verify emergency procedures, integrate power and communications, certify ventilation performance, and run trial operations before passenger service begins. That period is often one of the most demanding parts of the schedule because the project has to function as a fully coordinated transport system, not just as a completed civil structure. Section 1 also has to be understood within the timeline of the larger D-Line extension program. It is the first of 3 major sections, meaning its completion has operational importance beyond its own stations. Once open, it becomes the base from which the later western sections connect toward Beverly Hills, Century City, Westwood, and eventually the VA campus. That makes Section 1 the first visible delivery of a longer strategic investment that has been advancing in phases. At John F. Kennedy International Airport, one of the most important US megaproject milestones in 2026 is the opening phase of the new Terminal 1, a major redevelopment on the airport's south side in New York. This project is designed to replace the former Terminal 1, Terminal 2, and the site of the former Terminal 3 with a single, much larger international gateway. It is one of the central pieces of JFK's broader airport transformation, and in 2026, the focus is on turning a long-running construction site into an operating terminal environment. The new Terminal 1 is planned as a large-scale international terminal with modern aircraft gates, expanded passenger processing space, upgraded baggage systems, new security screening areas, and infrastructure designed for wide-body aircraft used on long-haul routes. Its importance comes from both scale and function. JFK is one of the main international entry points into the United States, and the terminal is being built to increase capacity, improve circulation, and support a more efficient border, customs, and airline operation than the older facilities it replaces. Construction work leading into 2026 is centered on delivering the first completed section of the terminal. That includes finishing the structural frame and enclosure of the initial concourses, completing interior fit-out, installing mechanical, electrical, and plumbing systems, testing baggage handling equipment, commissioning airfield side systems, and preparing passenger processing zones for operation. Road access, curbside works, utility connections, and apron. Infrastructure also need to be completed in sequence, so the first phase can function as a live airport terminal rather than just a finished building shell. A major challenge is that this work is being carried out inside one of the busiest aviation environments in the country. Construction has to be staged around active aircraft movements, existing terminal operations, security restrictions, and strict commissioning requirements. That makes 2026 especially important because the project must shift from heavy civil and structural work into testing, certification, operational readiness, and phased turnover. In airport megaprojects, that transition is often the most difficult part, since systems integration matters as much as the building itself. For a video about US megaprojects completing in 2026, the new Terminal 1 fits best as a project reaching a major completion milestone in that year, rather than its absolute final build-out. The first operating phase is expected in 2026, while the full terminal program continues beyond that initial opening through later phases. That means 2026 is the year when the project begins delivering real passenger capacity, even though additional gates, support areas, and final expansion elements may continue afterward. In Northern California, the BART Silicon Valley. Phase 2 project is one of the largest transit expansions associated with the next stage of US infrastructure delivery. But for a video about United States megaprojects completing in 2026, it has to be described carefully because this project is better understood as a major construction program, advancing toward later delivery milestones rather than a simple single-year completion story. Its purpose is to extend Bay Area rapid transit from the Berryessa/North San Jose area farther into Santa Clara County through downtown San Jose and on to Santa Clara, creating the long-planned rail connection between the regional BART network and the core of Silicon Valley. The project is significant because it is not just a surface rail extension. It is built around a complex urban alignment that includes substantial tunneling, underground station construction, systems integration, and interface work in one of the most constrained and economically important urban corridors in the United States. The extension is planned to add several new stations, including underground stops in central San Jose, and it is intended to connect major employment districts, regional transit facilities, and dense urban destinations that have historically lacked direct BART service. For a 2026-focused mega project segment, the relevant point is the construction work being done in 2026 to move the program toward its final outcome. That work is expected to center on major civil construction, utility relocation, excavation support, station box development, tunnel-related preparation or advancement, structural concrete operations, systems facility construction, and the continuing build-out of rail infrastructure elements needed for later operating service. On a project of this scale, 2026 is the kind of year in which visible progress comes from heavy engineering execution rather than ceremonial opening. Contractors and agencies would be focused on sequencing underground works, maintaining traffic and utility service above active construction zones, and preparing the corridor for the later installation of track, power, ventilation, communications, and life safety systems. And its importance lies in scale, network logic, and the number of separate construction fronts advancing at the same time. Rather than a single metro extension, it is a new orbital and cross-suburban rapid transit system being built around Paris to restructure mobility across the wider metropolitan region. The program includes new automatic metro lines, major line extensions, dozens of new stations, large interchange hubs, new maintenance sites, and extensive tunnel infrastructure intended to connect outer suburbs directly without forcing passengers through central Paris. The project is designed to address a structural weakness in the existing Paris transport network. Historically, many journeys between suburban areas required travel inward toward the center and then back outward again, creating inefficiency, crowding, and long journey times. The Grand Paris Express changes that pattern by building new circumferential and tangential routes. Its main components include Line 15, forming a large orbital route around the capital, together with Lines 16, 17, and 18, which extend automated metro service into areas that previously lacked rapid, high-capacity links of this type. The program also includes major extensions to existing Line 14, which plays a strategic role in redistributing passenger flows. In 2026, construction activity is still active across multiple sections, although the exact stage varies by line and segment. Some parts are in advanced systems and station fit-out phases, while others remain defined by civil engineering. The year includes continued tunnel excavation in unfinished sectors, structural completion of station boxes, installation of track slabs, platform systems, power supply equipment, ventilation, fire safety systems, signaling, communications, drainage, and architectural fit-out. At the same time, works continue on shafts, emergency access points, technical buildings, depots, and surface-level integration around station sites. The project, therefore, combines underground heavy civils with railway systems, engineering, and urban redevelopment in parallel. A major distinguishing feature of the Grand Paris Express is the complexity of building inside an already dense metropolitan environment. In 2026, construction is not only about boring tunnels, it also involves managing interfaces with existing metro, RER, suburban rail, roads, utilities, and dense urban districts. New stations are often being built as interchange structures beneath or beside active transport infrastructure, which increases engineering difficulty and extends delivery timelines. Ground conditions, utility diversions, and urban constraints all influence the pace of work. Because of this, the program is best understood as a sequence of interrelated megaprojects under one name rather than as one uniform construction site. Timeline is central to any accurate description of the project in 2026. The Grand Paris Express is being delivered in phases rather than opening all at once. Some sections have already moved closer to operation earlier than others, especially where they are tied to strategic deadlines or have more advanced civil completion. Other sections remain scheduled for later delivery in the second half of the 2020s and into the early 2030s. That means completion depends on which line is being discussed. In broad terms, 2026 is a year of mixed progress, commissioning and finalization on some stretches, full full construction on others, and continued network integration across the program as a whole. Spanning Estonia, Latvia, and Lithuania, Rail Baltica in 2026 is one of Europe's most important cross-border transport megaprojects still under construction, because it is designed to build an entirely new high-speed standard gauge railway through a region whose historic rail system largely developed to a different gauge and for different geopolitical and economic patterns. The project is not a conventional upgrade of an existing main line. It is a new north-south rail corridor intended to connect the Baltic states more directly with Poland and the wider European rail network for both passenger and freight transport. The strategic purpose of Rail Baltica is broader than travel time reduction alone. It is meant to integrate the Baltic states into the European standard gauge system, increase freight capacity, improve military and logistical mobility, and strengthen transport resilience along the eastern flank of the European Union. The corridor is planned to link Tallinn, Pärnu, Riga, Panevėžys, Kaunas, and the Polish border, with associated connections to airports, intermodal terminals, freight facilities, and urban stations. Because of that scope, Rail Baltica is best understood as a corridor program made up of many separate civil, structural, and systems contracts rather than one single construction site. In 2026, construction is underway on multiple fronts, but progress is uneven by country and by section. The year is defined by a combination of large-scale earthworks, embankment formation, bridge and viaduct construction, station and terminal development, access road works, utility relocations, drainage systems, and the continuing build-out of substructures for future track installation. In some sections, 2026 involves preparation of the railway formation and the structural completion of crossings over roads, rivers, and existing rail lines. In other sections, work is focused on station zones, airport interchanges, depot-related facilities, and environmental mitigation. The project's complexity comes from the fact that each national segment moves through procurement, land acquisition, and physical construction at a different pace. One of the central engineering features of Rail Baltica is that it requires a new railway geometry suitable for modern, high-speed passenger service and efficient freight operations. That means straighter alignments, grade-separated crossings, new bridges, new signaling systems, and a corridor designed to standards different from much of the existing regional rail network. In 2026, the visible construction is therefore not only about track, it also includes fencing, noise barriers where needed, road overpasses, underpasses, culverts, drainage channels, subgrade improvement, and the preparation of technical systems that will later support electrification, communications, and train control. Rather than a single continuous railway built exactly as first proposed, HS2 in 2026 is a partially redefined high-speed rail mega-project still under construction in the United Kingdom, centered on the line between London and the West Midlands, and on the large station, tunnel, viaduct, earthworks, and systems packages required to make that first phase operational. Within a survey of Europe's mega-projects under construction in 2026, HS2 remains significant because of both its scale and the extent to which it is reshaping transport infrastructure, land use, and rail capacity in Britain even after major scope changes. The project's main purpose is capacity as much as speed. Britain's classic main lines, especially the West Coast Main Line, carry a mix of intercity, commuter, and freight traffic that limits flexibility. HS2 is intended to move part of the long-distance passenger demand onto a separate high-speed railway, freeing space on existing routes for additional commuter and freight services. In engineering terms, that requires a new purpose-built corridor with straighter alignments, major grade separation, dedicated stations or station alterations, and extensive civil works through densely populated and environmentally sensitive areas. By 2026, the active construction focus is on Phase 1 infrastructure between the London area and the West Midlands. This includes continued work on major viaducts, embankments, cuttings, bridges, tunnel drives, tunnel fit-out, retaining structures, drainage, utility diversions, and route-wide civil engineering needed to form the railway corridor. On the station side, construction activity continues at key locations such as Old Oak Common in West London and Birmingham Curzon Street, together with interchange-related works in the West Midlands. In underground sections, the project still involves tunnel boring, segment lining, portal construction, ventilation and emergency access structures, and later stage internal preparation for railway systems. In surface sections, 2026 work includes track bed formation, structural completion of bridges and viaducts, and progressive transition from heavy civils toward railway installation on completed stretches. A defining feature of HS2 in 2026 is that it is no longer understood as the full original network concept. The London to Birmingham section remains the core delivery program, while northern extensions that were once central to the overall plan have been cancelled or fundamentally altered. That makes the timeline more specific. Construction in 2026 is directed toward completing the first operational route rather than toward building the entire originally proposed Y-shaped national network. This distinction is essential in any accurate description of the project during that year. The program timeline has shifted repeatedly. The project moved from early preparation and land acquisition into full-scale civil works in the 2020s. But cost growth, political review, and scope reductions changed the schedule. By 2026, the line is still not near immediate opening. It remains in a prolonged delivery phase involving both unfinished structures and complex systems integration still to come. The expected completion and opening of the London West Midlands route is generally placed in the early to mid-2030s rather than the original earlier targets. Final timing depends on the pace of civil completion, installation of track, power, signalling, testing, and commissioning across the route and stations. Unlike conventional rail expansion projects, Stuttgart 21 is a complete reconfiguration of a major urban and regional rail node, while the city around it continues operating. In the context of Europe's megaprojects under construction in 2026, it remains one of the continent's most important and most complex railway transformations, centered on replacing Stuttgart's historic above-ground terminus with a new underground through station and reorganizing the rail approaches across the wider region. The core concept is operational rather than architectural. The existing terminal layout forces many trains to end and reverse direction in Stuttgart, which limits capacity and slows long-distance and regional traffic. Stuttgart 21 converts the city into a through-running hub. The centerpiece is the new underground station, designed with 8 platform tracks set beneath the city, linked to a large network of new approach tunnels. This change is intended to improve network efficiency, reduce route conflicts, and support faster services on north-south and east-west corridors. By 2026, the project is still in an advanced construction and systems integration phase rather than an early excavation phase. The most visible work in that year includes continued fit-out of the underground station structure, completion of track systems, installation of overhead electrification and signaling equipment, tunnel finishing works, fire and life safety systems, ventilation, drainage, and extensive testing of railway operations infrastructure. Civil works are not the only focus anymore. A large share of the effort in 2026 is on converting completed structures into an operational railway environment that includes technical rooms, control systems, escape routes, platform equipment, and connections between the station box and the surrounding tunnel network. Another major part of the scheme is the set of new lines and tunnels connecting Stuttgart to the wider region. These include long rail tunnels through difficult geology and links toward the airport, the Messe area, and the Wendlingen-Ulm high-speed route. In 2026, works are still associated with completing these interfaces, finalizing rail equipment, and preparing the network for commissioning. The project is not just one station. It is a coordinated package of underground urban rail infrastructure, regional access routes, and integration with one of Germany's major high-speed corridors. Timeline remains central to how Stuttgart 21 is understood. The project has been discussed, redesigned, and contested for many years, with construction stretching far beyond the original expectations. By 2026, it is generally in its final major delivery period, but full completion depends not only on building works, but also on testing, approvals, and readiness across interconnected sections. The main commissioning target has been placed in the second half of the 2020s, with opening commonly associated with 2026 for key elements, although some related components and follow-on works may extend beyond that point depending on operational readiness. At the center of Europe's north-south transport system, the Brenner-based tunnel remains one of the most important megaprojects still under construction in 2026. The project is being built beneath the Alps between Austria and Italy to create a new, low-gradient railway connection under the Brenner Pass, one of the busiest freight and passenger corridors crossing the mountain barrier between northern and southern Europe. Its strategic function is to shift more long-distance freight from road to rail, increase line capacity, and improve journey times on the Scandinavian-Mediterranean transport corridor. The main tunnel system is designed as a base tunnel rather than a summit route, meaning trains pass through the mountains at a much lower elevation than on the historic Brenner line. This reduces gradients and allows heavier and longer freight trains to move more efficiently. The core structure consists of two main railway tubes running in parallel, connected by cross passages for safety and maintenance, together with an exploratory tunnel that has also served as a geological investigation and drainage structure during construction. When combined with the existing Innsbruck rail bypass, the continuous underground rail link reaches a total length that places it among the longest railway tunnel systems in the world. In 2026, construction activity is still focused on full-scale underground excavation, lining, structural completion, and railway systems, preparation across multiple lots on both the Austrian and Italian sides. Tunnel boring machines and conventional drill and blast methods have both been used depending on geological conditions. Work in 2026 includes further breakthrough progress in unfinished sections, waterproofing, final concrete lining, installation of invert slabs, construction of emergency and technical caverns, and continued development of cross passages between the main tubes. At the same time, interior works advance in completed stretches, including drainage infrastructure, cable routes, ventilation-related systems, and preparation for later installation of track, power, signaling, and communications equipment. Megaprojects remains the Fehmarn Belt fixed link, the undersea connection being built between Rødbehaven in Denmark and Puttgarden in Germany. Rather than a bridge, this project is a 17.6-kilometer immersed tunnel designed to carry both a double-track electrified railway and a 4-lane motorway beneath the Fehmarn Belt Strait. Its purpose is to remove one of the main bottlenecks between Scandinavia and continental Europe and to create a faster, more direct corridor for passengers and freight moving through the north-south axis of the continent. The construction method is what makes the project technically distinctive. The tunnel is being built from large prefabricated concrete elements produced on land at a purpose-built factory site near Rødbehav. These massive sections are cast in controlled conditions, fitted out internally, floated into position at sea, and then submerged into a dredged trench on the seabed. Once aligned and connected, they are covered and protected, creating a continuous immersed tunnel structure. This approach avoids the need for a long bored tunnel while also reducing exposure to the weather conditions that would affect a major bridge in the Baltic. In 2026, the project is still defined by heavy marine and civil engineering activity on both sides of the strait. Work in that period includes continued fabrication of standard tunnel elements and special service elements, dredging and preparation of the tunnel trench, installation of completed elements in sequence, expansion of the portal structures, and large-scale land works connecting the immersed tunnel to the Danish and German transport networks. At the same time, rail and road approach infrastructure, technical building, power systems, drainage, and safety installations continue progressing in parallel because the tunnel itself cannot operate without fully integrated links to the surrounding network. The railway component is especially important in the broader European context. The fixed link is intended to reduce travel times significantly between Denmark and Germany and to strengthen freight capacity on a route that currently depends depends on ferry services. For passenger rail, the link is expected to support faster journeys between Copenhagen and Hamburg. For freight, it is meant to provide a more reliable and higher capacity crossing that fits into the wider Scandinavian Mediterranean transport corridor. The timeline attached to the project has long been central to its importance. After years of planning, approval processes, environmental review, and preparatory works, the main construction phase moved into large-scale execution in the first half of the 2020s. The widely stated target has been opening around the end of the decade, with completion generally associated with 2029, although final commissioning depends on tunnel installation, systems testing, and the readiness of the connected rail upgrades, particularly on the German side. At the center of North Texas's expanding regional rail network, the Dart Silver Line stands as one of the most complex transportation megaprojects under construction in the Dallas region in 2026. Unlike traditional light rail lines, the Silver Line is being delivered as a commuter-style corridor designed to connect suburban employment centers, major airports, and existing rail systems across multiple cities in Collin, Dallas, and Tarrant counties. The Silver Line is a roughly 26-mile east-west rail corridor stretching from Shiloh Road in Plano to DFW Airport North Station. It repurposes and upgrades an existing freight rail right-of-way, requiring extensive coordination between passenger rail construction and ongoing freight operations. This shared corridor condition defines much of the construction activity occurring in 2026, making the project significantly more complex than greenfield rail lines. By 2026, the Silver Line is firmly in its peak construction phase. Track installation and rehabilitation are ongoing across multiple segments, including full replacement of rail, ties, ballast, and drainage systems to meet passenger rail standards. In several areas, parallel tracks are being added or extended to allow freight and passenger trains to operate simultaneously without service conflicts. These works require nighttime construction windows and precise scheduling to minimize disruption. Station construction is a major focus during 2026. All planned stations serving Plano, Addison, Carrollton, Capel, and DFW Airport are in various stages of vertical construction. Platform structures, canopies, elevators, stairways, and pedestrian bridges are being built concurrently at different sites. In 2026, crews are installing structural steel, pouring elevated platforms, and beginning architectural finishes at stations that reached foundation completion in earlier years. Grade crossing reconstruction defines another major category of 2026 construction. Dozens of roadway crossings along the corridor are being rebuilt or upgraded with new signaling systems, gates, medians, and roadway geometry. Some crossings are being closed or consolidated entirely to improve safety and reduce long-term maintenance. These works require coordination with local municipalities and involve phased traffic shifts that extend throughout the year. Bridge and structure work continues through 2026 at multiple locations. Existing rail bridges are being widened, reinforced, or replaced to support increased rail traffic and modern load requirements. In flood-prone areas, embankments and culverts are being rebuilt to improve resilience against extreme weather events. These civil works represent some of the most capital-intensive portions of the project. Systems installation accelerates significantly during 2026. Crews are deploying signaling and train control systems designed for higher speed regional rail service. This includes centralized traffic control infrastructure, communication systems, and safety monitoring equipment. Fiber optic networks are being installed along the corridor to support real-time operations, dispatching, and passenger information systems. From a timeline perspective, 2026 is a transition year between heavy civil construction and operational readiness. While earthwork and major structures dominate early phases of the project, 2026 sees a shift towards systems integration, station completion, and corridor-wide testing preparation. Track work and signaling installation continue into 2027, followed by extensive testing and certification. Revenue service is not expected to begin in 2026. Instead, late 2026 and 2027 are dedicated to system testing, operator training, safety certification, and coordination with freight rail partners. Full passenger service is anticipated after completion of these phases, with opening targeted in the latter part of the decade, contingent on testing and regulatory approval timelines. Within the broader context of Dallas megaprojects under construction in 2026, the DART Silver Line is distinct for its regional impact rather than visual prominence. It directly connects major job centers, suburban cities, and DFW Airport without requiring transfers through downtown Dallas. Its construction reshapes an existing rail corridor into a modern passenger system, expanding mobility options across one of the fastest-growing metropolitan regions in the United States.
Brightline West isn't an idea. It's under construction. A $12 billion high-speed rail megaproject designed to link Los Angeles to Las Vegas in just over 2 hours, cutting a trip that often takes over 5 by car. With speeds reaching 200 miles per hour and over 260 miles of new rail corridor, this is one of the largest and most complex infrastructure projects ever attempted in the American Southwest. The alignment runs primarily along the I-15 corridor, chosen for its straight path, existing right-of-way, and the massive volume of traffic it sees. Over 50 million people travel between LA and Las Vegas each year, many of them stuck in stop-and-go congestion. Building next to a major interstate, however, comes with logistical and engineering demands on a different scale. Crews must work within narrow margins between freeway traffic and construction zones, requiring extensive concrete barriers, temporary detours, and phased sequencing to avoid bottlenecks. The trains will operate entirely on dedicated, grade-separated track. That means no level crossings, no signal delays, and no sharing with freight or commuter rail, making Brightline West a true high-speed rail system by global standards. To achieve this, over 300 structures are being constructed along the route, including overpasses, bridges, wildlife crossings, and viaducts. Every one of them is engineered to withstand extreme desert heat, high wind speeds, and seismic loads consistent with California building codes. One of the most technically demanding sections involves crossing the Kaijon Pass, an elevation climb of over 3,000 feet between the Inland Empire and the high desert. This stretch requires extensive cut-and-fill operations, retaining walls and reinforced embankments. Specialized track design, including banked curves and controlled gradients, ensures that trains maintain high speeds without overstressing the vehicles or the infrastructure. Trackbed construction is another layer of complexity. Unlike conventional rail, high-speed systems require exacting tolerances for smoothness and alignment. The subgrade must be compacted and stabilized to millimeter-level accuracy, followed by multiple layers of ballast, reinforced concrete slab track, and vibration-damping materials. These systems are monitored in real time through embedded sensors, allowing for predictive maintenance and immediate response to deviations. Powering the system is an electrified catenary line running the full length of the corridor. This requires constructing hundreds of miles of new transmission infrastructure, including substations, overhead gantries, and high-voltage feeds. To ensure uninterrupted service, the power supply is designed with built-in redundancy and real-time switching capabilities. Utility coordination across 2 states and multiple counties adds further layers of complexity to every mile built. The train sets themselves, based on Siemens Velaro or similar European high-speed rail platforms, will be custom modified for American standards. Each unit will feature aerodynamic nose cones, regenerative braking systems, crash energy management structures, and lightweight aluminum bodies to reduce axle load and track wear. These aren't commuter trains. They're precision-built machines designed to run at 200 mph across open terrain, with acceleration, deceleration, and safety systems modeled after Japan's Shinkansen and Germany's ICE. In 2026, one of San Francisco's most strategically important megaprojects under construction is taking shape across the Caltrain rail yards in the heart of central Soma. This isn't just a housing or transit upgrade. It's a massive reimagining of over 20 acres of publicly owned rail-adjacent land that has long divided the neighborhood. As construction pushes ahead this year, the rail yard redevelopment is steadily moving from planning to reality, with early phases under active build-out and long-term infrastructure elements aligning with the city's broader transit goals. Right now in 2026, the site is in the thick of foundational construction. Crews are laying the groundwork, literally, for what will eventually be a dense, mixed-use district layered above and around the working Caltrain tracks. This megaproject is part of a coordinated effort to modernize regional transportation while unlocking thousands of new homes and millions of square feet of development potential just blocks from downtown San Francisco. The Caltrain yard has been a physical and visual barrier in central Soma for generations. But in 2026, construction is actively transforming this space into an urban connector. Elevated platforms, decked structures, and street-level improvements are all in progress, designed to bridge the gap between surrounding neighborhoods and the core rail infrastructure. This year, much of the work focuses on realigning utilities, stabilizing the site for future vertical construction, and preparing parcels that will be used for new housing, office towers, and public spaces. The housing element of the rail yard redevelopment is one of the most anticipated components currently under construction. Phase 1 will deliver several hundred new residential units, with a significant portion allocated for affordable housing. These buildings, now rising on the edges of the yard, are expected to be ready for occupancy by 2028. Eventually, the full build-out will add thousands of homes to one of the city's most transit-rich locations, housing that is critically needed as San Francisco continues to face supply pressures. But housing is only one piece of this megaproject. In 2026, work is also underway on commercial development that will bring job space to the corridor, particularly targeting sectors like life sciences, tech, and creative industries. The close proximity to both downtown and future rail connections makes this site highly desirable, and the ongoing construction reflects the urgency to activate it. Several mid-rise office buildings are being framed out this year, with completion of the first wave of commercial space projected around 2029. A crucial component that's being integrated into the redevelopment in real time is transportation. The Caltrain facility itself is being reconfigured to prepare for electrification, high-speed rail integration, and potential undergrounding as part of the downtown rail extension. In 2026, while major tunneling has not yet reached the yard, planning and structural coordination are fully underway to make sure future rail service, including high-speed trains, can be accommodated. This makes the rail yard site not just a place to live and work, but a critical node in the future of statewide transit.
Buried beneath the heart of London, there's a railway line that took more than 2 decades to go from vision to reality. And when it finally opened, it didn't just change how people travel across the city, it redefined what a modern urban railway could actually be. This is the story of the Elizabeth Line, better known during its construction as Crossrail, and it's one of the largest infrastructure projects the UK has ever attempted. What makes it so extraordinary isn't just the scale, though with over 100 kilometers of track and 10 brand new stations, the size alone is staggering. It's the complexity of tunneling through one of the most congested urban landscapes on Earth. London's underground is a tangled web of subways, sewers, gas mains, historic foundations, and centuries of construction. And Crossrail had to slide right through that chaos without disturbing the city above. That meant custom-designed tunnel boring machines carving through clay and chalk just inches away from existing infrastructure, operating with millimeter-level precision. And in the middle of all that, engineers were building cathedral-like stations deep underground, complete with massive concourses, soaring escalators, and sleek modern finishes that feel more like an airport than a subway. But it wasn't just about digging tunnels. Crossrail had to knit together a patchwork of existing railways to create a single high-capacity line running from Reading and Heathrow in the west, through central London, and out to Shenfield and Abbey Wood in the east. That meant not just physical connections, but totally revamping old lines, upgrading signals, rebuilding platforms, and bringing everything into one unified system. And because it's a hybrid of commuter rail and metro, the trains themselves had to be custom built, longer than anything else running in London. Fully walk-through from end to end, with cutting-edge safety and digital systems running the show behind the scenes. Of course, none of this came easy. The project was delayed, over budget, and constantly under scrutiny. It was originally meant to open in 2018, but it didn't fully launch until 2022. And even then, services were phased in slowly over time. But when it finally opened its doors, the impact was immediate. Journey times across London dropped dramatically. The central section now cut straight through the city in minutes, bypassing the old, overcrowded tube lines and offering a much smoother ride for millions of passengers. In fact, the Elizabeth line has already become one of the busiest railways in the entire UK, and it's reshaping real estate patterns, job access, and urban development all along its route. At its core, Crossrail isn't just a transport upgrade, it's a statement. A bet that even in an old, densely built city like London, there's still room to dream big, to build something transformative, and to prove that world-class engineering can still punch through centuries of constraint.
The Metro Regional Connector is just 1.9 miles long, but its impact ripples across the entire Los Angeles basin. Beneath the chaotic sprawl of downtown, this subterranean link has silently transformed the backbone of the city's transit network. Not with flashy architecture or sweeping overpasses, but with precision tunneling and deep engineering ambition. It's a megaproject built not to be seen, but to be felt, every time a train glides through the city uninterrupted. Before this connector existed, Los Angeles had a problem. Its growing light rail system, the A, E, and L lines, stopped short of being truly regional. Trains terminated downtown, forcing commuters to transfer between lines, often in disconnected stations, wasting time and discouraging use. The system worked technically, but it didn't flow. It didn't breathe. The regional connector changed that. By boring two parallel tunnels through the dense urban core and tying together these once isolated lines, it created the first true one-seat ride across the county. Now a passenger can board in Azusa and ride directly to Long Beach. East Los Angeles to Santa Monica, no transfers, no transfer platforms, just a straight shot through the city's heart. It's a small piece of track, but a massive leap in connectivity. But connecting three major lines under a century-old city is anything but simple. Downtown LA is layered in complexity, filled with pre-existing tunnels, water mains, sewers, building foundations, earthquake faults, and a living, breathing population above. To carve a clean path through all of it, engineers had to think in three dimensions, navigating not just forward, but over, under, and around everything in their way. The answer came in the form of two tunnel boring machines, Angeli, and Elsie. Each one was a 1,000-ton beast, stretching over 400 feet long, with rotating cutter heads capable of grinding through soil, rock, and buried urban history. But the real trick wasn't speed, it was control. Tunneling through this part of LA meant passing just feet beneath sensitive structures like the historic Broadway corridor and active subway lines, where even the slightest misalignment could cause cracks or settlement. So crews worked slowly, methodically. Pressurized faces on the TBMs stabilized the ground ahead. Real-time monitoring systems tracked every vibration and movement, sending feedback to operators above. In some segments, the margin for error was less than an inch. It was engineering done with surgical precision, buried beneath a city that never stopped moving. At the surface, the work was just as intense. 3 brand new underground stations were constructed: Little Tokyo Arts District, Historic Broadway, and Grand Avenue Arts, Bunker Hill. Each of them had to be excavated in tight quarters, often amid live traffic, aging buildings, and pedestrian zones. The Little Tokyo station posed one of the greatest challenges. Crews had to demolish the existing above-ground station, reroute the tracks underground, and do it all while preserving the cultural heart of a vibrant neighborhood.
Far south of Dallas, in Ellis County, near the city of Midlothian, the Google Data Center campus stands as one of the most infrastructure-intensive megaprojects under construction in the North Texas region in 2026. Unlike high-visibility urban developments, this project is defined by scale, power demand, and systems complexity, with construction activity focused on creating long-term digital infrastructure rather than public-facing architecture. The Midlothian Data Center is part of Google's broader expansion of hyperscale computing capacity in Texas, selected for its access to land, transmission infrastructure, and regional redundancy. The site is planned as a multi-building campus rather than a single structure, allowing phased expansion over several years. This phased approach makes 2026 a key construction year, as initial facilities transition from shell construction to systems-heavy build-out. By 2026, site-wide civil and utility infrastructure is largely established, enabling vertical construction and interior fit-out to dominate activity. Primary data hall buildings are either topped out or approaching structural completion, with reinforced concrete frames and steel roof systems designed to support heavy mechanical loads. These structures prioritize clear spans, high floor loading capacity, and modular expansion potential. Mechanical and electrical construction is the defining feature of 2026 work. Crews are installing large-scale power distribution systems, including substations, switchgear yards, and redundant electrical pathways. Multiple layers of redundancy are built into the campus, requiring parallel systems for primary and backup power. This includes integration with regional transmission lines and on-site backup generation infrastructure. Cooling infrastructure is another major focus during 2026. Data center cooling plants, including cooling towers, chillers, and water treatment systems, are under active construction. These systems are designed to handle continuous high-density server loads while optimizing water and energy efficiency. Piping networks connecting cooling plants to individual data halls are installed underground and within service corridors throughout the campus. Interior build-out of data halls accelerates in 2026. Raised floor systems or slab-integrated airflow designs are installed depending on building configuration. Server rack infrastructure, cable trays, and fire suppression systems are constructed in tightly sequenced phases. Fire protection systems typically use specialized suppression methods designed for sensitive electronic environments, requiring extensive testing and commissioning. Support buildings and ancillary facilities are also under construction in 2026. These include network operations centers, security facilities, maintenance buildings, and office space for on-site technical staff. These structures are less visually dominant, but critical for day-to-day operation and monitoring of the data center campus. Security and perimeter infrastructure advances significantly during 2026. The site includes layered physical security systems such as perimeter fencing, controlled access points, surveillance infrastructure, and secure internal zoning. Much of this construction is integrated into site grading and landscaping to maintain operational separation without excessive visual impact. Water and environmental infrastructure remains active throughout 2026. New water supply connections, storage tanks, and wastewater systems are completed or expanded to support cooling operations. Stormwater management features, including retention ponds and drainage systems, are finalized to meet regulatory requirements and protect surrounding land from runoff impacts. From a timeline perspective, 2026 represents a transition from heavy shell construction to commissioning-focused activity. While new buildings may still be under construction, several completed structures enter systems testing phases. Electrical load testing, cooling system commissioning, and network validation are conducted incrementally as each facility segment reaches readiness. Construction activity is expected to continue beyond 2026, with additional data halls and support facilities added in subsequent phases. Full campus build-out is typically planned over multiple years, allowing capacity to scale with demand. Initial operational capability is often achieved before total completion, with sections of the campus coming online independently.
In 2026, one of the most visually dramatic megaprojects under construction in San Francisco is the redevelopment of the Potrero Power Station site. Rising on a stretch of industrial waterfront in the Dogpatch neighborhood, this 29-acre site is being transformed from a rusting relic of the city's energy past into a dense, mixed-use community that blends housing, innovation space, and public waterfront access. After decades of inactivity and pollution, the area is now filled with active construction, with multiple buildings rising around the preserved smokestack that once powered large parts of San Francisco. This year marks a turning point in the project's timeline. Key infrastructure has been installed, roads are taking shape, and vertical construction is advancing on several residential and commercial buildings. The first wave of occupancy is expected in 2027, while full build-out of the project will continue into the early to mid-2030s. In terms of current construction activity, 2026 is the first year where the scale and form of the new neighborhood are clearly emerging on the skyline. The development plan includes over 2,600 residential units, 20% of which are designated as affordable, along with office space, labs, retail, cultural venues, and a massive new waterfront park. In 2026, at least 4 parcels are under active construction, with cranes on site, facades being installed, and streetscape work underway to connect the site to the surrounding Dogpatch and Pier 70 developments. The power station's original brick boiler house is being stabilized and preserved to eventually be converted into a centerpiece public building, part of a broader trend in the project to mix new construction with industrial heritage. The Potrero Power Station site has long been one of the last undeveloped pieces of San Francisco's southeastern waterfront, and in 2026, it's becoming a key node in a chain of megaprojects that are physically reconnecting the city to its shoreline. The public realm is a major focus of the construction, with waterfront promenades, plazas, and parks currently being graded and landscaped to open in stages beginning in 2028. These green spaces are designed not just for beauty, but for resilience, integrated with sea level rise protection and sustainable stormwater systems. A major portion of the site is also being prepared for future commercial tenants in the life sciences and advanced technology sectors. In 2026, lab-ready office space is under construction, with leasing expected to begin the following year. These facilities are a core part of the Megaprojects' economic impact, offering high-tech employment opportunities and reinforcing San Francisco's role in the Bay Area Innovation Corridor. Construction in 2026 is being carried out with strict environmental oversight, given the site's legacy as a fossil fuel power plant. Soil remediation, groundwater treatment, and air quality monitoring are ongoing as each new section of the site is prepared for development. This adds complexity, but also makes the transformation more significant, turning a brownfield into a 21st century neighborhood that meets the city's housing and sustainability goals. When fully completed, the Potrero Power Station will be a dense, transit-rich waterfront extension of the city, blending over 6 acres of parks, thousands of homes, and over 1 million square feet of office and retail space into a single cohesive community. In the landscape of San Francisco's 2026 megaprojects, it stands out for its mix of industrial past and future potential. Every structure rising here is part of a deliberate effort to reshape how cities evolve, from polluted infrastructure into vibrant, livable places. Tucked just south of downtown Los Angeles, Exposition Park has always been a place of ambition, home to world-class museums, the LA Memorial Coliseum, and the beating heart of the city's cultural and sporting life. But what's unfolding there now isn't just an upgrade. It's a full-scale transformation, timed to align with the arrival of the 2028 Olympic Games. This is the Exposition Park expansion, and it's one of the most concentrated, multi-layered megaprojects happening anywhere in the city. We're talking about more than 100 acres of dense, high-profile development, the kind of space where architecture, infrastructure, landscape, and engineering have to work in seamless coordination. And every inch of it is being reimagined, stitched together into a new kind of urban park, one that blends Olympic-scale sports facilities with civic space, transit access, and cultural presence. At the center of this expansion is the Lucas Museum of Narrative Art, an enormous, fluid, almost spaceship-like structure that defies traditional design logic. Spanning over 300,000 square feet, the building floats above the landscape on concrete pylons, allowing for an uninterrupted park to run beneath it. Engineering that vision into reality meant solving a long list of structural challenges. The museum's form curves and bends with few right angles, requiring a steel skeleton unlike any conventional grid. Every beam had to be custom fabricated. Load paths had to be recalculated from scratch. But that's only one piece. Adjacent to it, new Olympic training facilities are being added in and around the Coliseum, including athlete, housing, high-performance sports labs, and temporary structures built to IOC standards. These aren't off-the-shelf projects. Each facility must meet international competition criteria while being adaptable for post-games public use. That means flexible infrastructure, modular designs that can expand or collapse depending on future needs, and utility corridors capable of serving both a global broadcast event and a local youth sports league. A new mobility hub is also under construction, tightly integrated with the K Line, Crenshaw LAX Line, regional bus service, and pedestrian corridors linking USC, the Natural History Museum, and BMO Stadium. This isn't just about moving people. It's about rethinking access. Engineers are embedding smart traffic systems, ADA upgrades, secure bike lanes, and crowd flow modeling to handle Olympic-scale surges without overwhelming local streets. Then there's the landscape itself. More than 14 acres of new green space are being carved into the existing grid, with bioswales, permeable pavement, and stormwater recycling systems hidden beneath sculpted terrain. Everything is dual purpose. That shaded plaza? It's also an emergency egress route. That rolling hill. It's backfilled over a utilities corridor with seismic isolation joints. Every tree and trail was designed not just for beauty, but for function, cooling microclimates, guiding crowds, and managing runoff during rare but intense LA storms. Beneath the surface, the engineering complexity continues. Utility upgrades, electric, water, fiber, gas, are being laid out like a circulatory system for a future-proof urban core. Crews had to dig and trench with surgical accuracy, often working just inches away from existing structures that couldn't be moved or shut down. Phasing the construction without interrupting events at the Coliseum or the Museum District meant round-the-clock scheduling, heavy prefabrication, and just-in-time delivery logistics.
Down on the shores of the Red Sea, where the old port city of Jeddah stretches out between desert and water, two enormous projects are quietly redrawing the map: Jeddah Central and Jeddah Economic City. Together, they represent a vision of transformation unlike anything the city has seen before, turning this historic gateway into a modern global hub for business, culture, and tourism. What makes these developments remarkable isn't just their scale, but the way they weave old and new, ambition and heritage, into something that feels distinctly Saudi, yet unmistakably international. Jeddah Central sits right in the heart of the city, taking over more than 5 square kilometers of waterfront that once housed the old desalination plant and underused industrial land. It's being reinvented as a new downtown, built around a sweeping marina and a waterfront district lined with cultural landmarks, residential towers, and entertainment spaces. The master plan revolves around 4 main landmarks: a sports stadium, an oceanarium, an opera house, and a museum, all designed to anchor Jeddah's identity as a cultural and leisure destination. Around them will rise luxury hotels, office towers, parks, and promenades, all connected by shaded walkways and open public spaces, meant to bring life back to the seafront. But this isn't just about aesthetics. The project's layout is designed around sustainability and smart urbanism, integrating renewable energy, green transport systems, and water recycling technologies suited to the coastal climate. It's a major shift for Jeddah, which has long struggled with congestion and uneven urban growth. The plan envisions a livable, walkable downtown that balances modernity with comfort, turning the Red Sea coast into a showcase for the new Saudi lifestyle that's emerging under the country's Vision 2030 framework. The idea is to create not just buildings, but experiences, places where art, commerce, and everyday life blend seamlessly. A short distance to the north, Jeddah Economic City takes that ambition and scales it up to a global level. This is the site of the Jeddah Tower, the skyscraper that aims to surpass 1 kilometer in height and become the tallest building in the world. The tower is the centerpiece of a vast mixed-use development covering more than 50 square kilometers, designed to serve as a new economic hub for trade, finance, and innovation. When complete, Jeddah Economic City will have residential neighborhoods, educational institutions, business districts, and green open spaces all linked together by advanced infrastructure and digital systems. The city's design places a strong focus on integration with the wider region. Ports, highways, and logistics corridors will tie it directly into the national network that connects Jeddah to Makkah, Medina, and eventually Neom, farther north. In many ways, Jeddah Economic City represents the country's broader push to diversify its economy beyond oil, creating new industries that can attract global investment and talent. Taken together, Jeddah Central and Jeddah Economic City show 2 faces of Saudi Arabia's urban transformation. One is cultural and civic, centered on lifestyle and heritage. The other is economic and technological, reaching for the future through engineering and ambition. Both are shaping a new identity for Jeddah, a city that once served as the gateway for pilgrims, now evolving into a gateway for ideas, enterprise, and modern urban life along the edge of the Red Sea. In the highlands of Ethiopia, right near the border with Sudan, a wall of concrete now stretches across the Blue Nile, a dam so massive that it's already reshaping not just the country's energy supply, but the politics of an entire region. This is the Grand Ethiopian Renaissance Dam, often shortened to GERD, and it's one of the most controversial and ambitious infrastructure projects in Africa's modern history. From a purely engineering standpoint, GERD is enormous. The main dam structure stands over 140 meters tall and spans nearly 2 kilometers across the Nile. Behind it, a reservoir capable of holding more than 70 billion cubic meters of water is slowly taking shape, making it one of the largest man-made lakes in Africa. And the hydroelectric potential is just as impressive. When fully operational, GERD is expected to generate over 6,000 megawatts of electricity. That's more than doubling Ethiopia's entire power capacity and turning the country into a potential electricity exporter for the whole East African region. But building this dam was never just about power. For Ethiopia, it's a matter of sovereignty and development. For decades, the country has relied on foreign energy imports and struggled to bring electricity to its rural population. GERD is seen as the key to unlocking long-term economic growth, creating jobs, supporting industry, and expanding access to power across millions of homes. It's a project that has been paid for largely through domestic funding, with the government encouraging citizens to invest in national bonds and support the construction financially and symbolically. That national pride, though, is matched by rising tensions downstream. Both Sudan and Egypt depend heavily on the Nile for irrigation, agriculture, and drinking water, and Egypt in particular has historically viewed the river as a lifeline. For generations, water treaties dating back to colonial times guaranteed Egypt a dominant share of the Nile's flow. Now, with Ethiopia holding back massive volumes of water behind a new dam, those old agreements are being tested. The fear from Cairo is that GERD could reduce the flow of water downstream, especially during the filling period of the reservoir, which could hurt Egyptian agriculture and water security. Ethiopia argues that the dam will actually help stabilize flow, reduce flooding, and benefit all three countries in the long term. But so far, years of negotiations haven't produced a final deal, and the disagreement has created real diplomatic friction, with threats, warnings, and political standoffs becoming more frequent. On the ground though, GERD is nearing completion. The first turbines are already spinning, and power is being delivered to the grid. Construction has taken over a decade, involving thousands of workers and a coordinated effort to bring in materials and equipment through difficult terrain. The logistics alone were staggering, given the remote location and the scale of the build. Whether GERD becomes a unifying symbol of African development or a long-term source of conflict depends on what happens next. Cooperation is still possible, but so is escalation. Downtown Dallas plays a central operational role in the World Cup, despite matches being hosted at AT&T Stadium in Arlington. The downtown core is designated as a primary fan destination, media hub, and hospitality center, requiring significant upgrades to handle international crowds, broadcast demands, and security requirements. As a result, construction in 2026 is distributed across transit corridors, public spaces, and city-owned facilities. Transportation upgrades are among the most visible construction activities in 2026. DART rail stations in and around downtown Dallas are undergoing platform improvements, accessibility upgrades, and system enhancements to accommodate higher passenger volumes. Construction includes platform resurfacing, expanded queuing areas, upgraded signage, and improved vertical circulation elements such as elevators and stairs. These projects are sequenced to maintain daily transit operations while accelerating work during off-peak periods. Street-level infrastructure work intensifies in 2026. Key downtown corridors are being reconstructed or modified to improve pedestrian safety, crowd flow, and curbside operations. Construction includes widened sidewalks, improved crosswalk geometry, upgraded traffic signals, and reinforced pavement sections designed to handle buses, service vehicles, and temporary event traffic. Utility relocations accompany much of this work, requiring coordinated trenching and phased restoration. Public space upgrades represent another major component of 2026 construction. Downtown parks, plazas, and open gathering areas are being improved to serve as fan zones and event staging areas. Construction includes new hardscape surfaces, lighting systems, temporary infrastructure tie-ins, and expanded power and data capacity. These upgrades are designed to be permanent, allowing spaces to function year-round after the tournament concludes. Security-related construction advances significantly in 2026. Downtown facilities designated for World Cup operations receive perimeter hardening, controlled access points, and upgraded surveillance infrastructure. This includes installation of security bollards, reinforced barriers integrated into streetscape design, and expanded camera and monitoring networks. Much of this work is intentionally blended into public realm improvements to avoid long-term visual impact. Hospitality and event support infrastructure also sees targeted upgrades during 2026. Convention and meeting facilities in downtown Dallas undergo interior renovations to support media, operations, team logistics, and international broadcasting. Construction includes upgraded power distribution, enhanced telecommunications infrastructure, improved loading and service access, and reconfigured interior layouts to support temporary World Cup users. Wayfinding and signage infrastructure is another major focus in 2026. Crews install new directional systems designed for international visitors, incorporating multilingual signage and standardized event iconography. These systems are integrated into streets, transit stations, and public buildings, requiring coordinated installation across multiple agencies and property owners. Technology infrastructure work peaks in 2026 as well. Downtown Dallas receives expanded fiber optic capacity, upgraded wireless networks, and enhanced data redundancy to support global media transmission and high-density mobile usage. These installations often occur underground or within existing structures, making them less visible but critical to World Cup operations. From a construction sequencing perspective, 2026 is the final and most intensive year of preparation. Many projects that began in earlier years reach substantial completion during this period, while others undergo final fit-out, testing, and commissioning. The goal is to have all core infrastructure operational well before the tournament begins to allow for trial events, system testing, and security exercises. Temporary infrastructure planning also overlaps with permanent construction in 2026. Areas designated for fan festivals and live viewing require embedded connection points for temporary stages, screens, and crowd management systems. Construction teams install these features during permanent upgrades to avoid disruptive temporary installations later.
Candlestick Point and Hunters Point Shipyard are among the most active megaprojects in San Francisco as of 2026. Spanning more than 700 acres along the city's southeastern shoreline, this redevelopment effort is in full swing, reshaping two long-neglected sites into a new urban district. Construction is progressing across multiple parcels, with new streets, housing blocks, and parks taking shape, setting the stage for what will become one of the largest residential and commercial expansions in San Francisco's modern history. At Candlestick Point, where the old stadium was demolished years ago, heavy machinery is grading land for the first wave of residential and retail construction. Multiple mid-rise buildings are rising along a newly gridded street layout. These early phases, expected to complete between 2027 and 2029, will include thousands of homes, many designated as affordable, as well as the backbone of a future retail corridor and public transit connections. Parks and green infrastructure are being built alongside housing, integrating sea level rise protections and climate-resilient landscaping directly into the urban form. To the north, at Hunters Point Shipyard, development is further along. Phase 1 construction is already well underway, with completed townhomes and condos beginning to fill with residents. Additional parcels are actively under construction in 2026, adding new units monthly. Commercial spaces, artist studios, and civic buildings are also under development. Part of the project's goal to restore not just housing, but economic vitality to a part of the city long cut off from opportunity. When fully built out in the early 2030s, the combined Candlestick Hunters Point project will deliver over 12,000 new homes, more than 300 acres of open space, and millions of square feet of office, retail, and cultural uses. It's a complete neighborhood emerging from land that was, for decades, contaminated, fenced off, and largely abandoned. What's distinctive about this project in 2026 is its physical and social scale. This isn't a small infill development or a single commercial tower. It's a city-scale expansion happening within the city limits. Infrastructure is being laid from scratch. Power grids, sewer lines, transit loops, and broadband networks are all part of the foundational work occurring now. Major sections of waterfront are being rebuilt with ecological restoration in mind, with plans for habitat zones, walking trails, and public piers that will eventually reconnect residents with the shoreline. Affordable housing is a central element of the development, and 2026 marks a critical point as the first large wave of affordable units nears completion. These are being reserved in part for legacy residents of Bayview Hunters Point, addressing historic displacement and economic exclusion. Community input remains part of the planning process, particularly in shaping local hiring programs and cultural preservation efforts. Construction challenges remain. Environmental safety is closely monitored due to the site's naval and industrial history. Some parcels require more remediation than others, which is influencing the pace of development. But in terms of raw activity, cranes, crews, and square footage under construction, Candlestick Point and Hunters Point Shipyard rank among the most dynamic megaprojects in San Francisco right now. The G Line, formerly known as the Orange Line, was never designed to stay the same. From the beginning, it was a workaround, a bus rapid transit route built in place of a rail line due to funding constraints and political compromise. But over time, its ridership and strategic location forced the city to rethink what it could be. Now the G Line is undergoing a major transformation, an infrastructure upgrade project spanning the entire 18-mile corridor through the San Fernando Valley, pushing the limits of what bus transit can do in Los Angeles. The goal is simple: increase speed, capacity, and safety. But executing that goal has required deep and complex engineering interventions at nearly every point along the route. One of the most critical changes is the installation of a state-of-the-art signal priority and preemption system. Unlike traditional traffic signals that respond to fixed timers or limited sensors, this system actively clears intersections ahead of approaching buses, reducing delays and allowing for smoother flow across dozens of street crossings. Another major element is the construction of grade separations. rail-style overpasses and underpasses at the busiest and most delay-prone intersections. Key locations like Sepulveda Boulevard, Van Nuys, and others are being excavated and rebuilt with concrete bridges and undercrossings to allow buses to pass through without ever stopping for cross-traffic. These structures require complex retaining wall systems, traffic rerouting, and in some cases, full reconstruction of local street infrastructure around the new grades. To support higher frequency service, the corridor is being outfitted with new power systems, bus-only lanes resurfaced with heavy-duty concrete, capable of supporting constant vehicle weight, and upgraded station platforms. The existing asphalt guideway, originally built to mimic light rail tracks in layout, has been deteriorating under the strain of articulated buses. Rebuilding it requires full-depth removal and replacement with reinforced concrete slabs, tied into a subsurface drainage system to prevent water intrusion and pavement shifting over time. Platform upgrades go beyond aesthetics. Stations are being lengthened to accommodate longer, higher-capacity buses and future electric models. Each platform is being raised and re-leveled to allow for near-zero gap boarding, speeding up passenger flow and improving accessibility. Integrated electrical conduits and utility vaults are also being installed during construction to prepare for future overhead charging systems as the fleet transitions to full electric. A core part of the upgrade involves upgrading the actual vehicle fleet. Metro is phasing in battery electric buses with larger passenger capacities, regenerative braking systems, and onboard diagnostics. These buses weigh more than their natural gas predecessors, which has direct implications for bridge loading, braking distances, and pavement wear. Engineers had to revisit structural tolerances across the entire corridor, from culverts and embankments to turning radii and clearance zones, to ensure long-term durability under heavier rolling stock. Fiber optic lines are also being laid alongside the corridor to support real-time monitoring. Everything from vehicle location, signal interaction, passenger load, and environmental data will be fed into Metro's central control center. This data will be used not just for dispatch, but to dynamically adjust signal cycles and reroute in case of emergencies. Drainage systems along the G line were never built for current-day storms. As part of the upgrade, culverts are being expanded, bioswales are being added to medians, and runoff channels are being lined with concrete and fitted with sensors to monitor flow levels during heavy rain. All of this is necessary to prevent trackway flooding and preserve the subgrade from erosion.
Rising high on the Ethiopian plateau, more than 2 kilometers above sea level, Addis Ababa has always been a city of layers. Old and new, formal and informal, chaotic and alive. But over the past few years, the city has begun to take on an entirely new shape. The Addis Ababa City Corridor and Smart City Project is the centerpiece of that transformation, a sweeping plan to modernize the capital, expand its infrastructure, and create a blueprint for what a 21st century African metropolis can look like. At its heart, the project is about connection. Addis Ababa has grown rapidly, with millions of people moving in from rural regions, but the city's layout and infrastructure never quite kept pace. Roads became crowded, neighborhoods expanded without clear planning, and public services struggled to keep up. The City Corridor Plan aims to tie it all together, a network of modern boulevards, transit routes, and green corridors stretching across the city, designed to integrate housing, commerce, and technology in one continuous urban system. Think of it as both a transportation project and a digital backbone, built to link everything from the city's financial district to its emerging industrial zones. The smart city component is what makes it truly forward-looking. It's not just about widening roads or adding new buildings. It's about embedding intelligence into the fabric of the city itself. Sensor-based traffic management, integrated public data systems, and sustainable utilities that can monitor and adapt in real time. Streetlights powered by solar panels, automated waste collection, water systems that track usage and detect leaks, and transport routes that update dynamically based on congestion. All of these features form part of the vision. Addis Ababa isn't just being expanded, it's being reprogrammed. Alongside the technology, there's also a strong architectural and social vision. The new city corridors are planned to include dedicated pedestrian paths, landscaped parks, and mixed-use developments that bring homes, offices, and public spaces together. Rather than separating zones by function, the aim is to create integrated communities that reduce the need for long commutes and support more sustainable living. It's a response to the sprawl that has defined much of the city's past growth, turning what used to be dusty, disconnected suburbs into modern, connected districts. The construction itself is happening in phases, with local and international teams working together to upgrade transport corridors, build smart infrastructure, and prepare new land for development. It's a massive logistical challenge involving coordination between ministries, tech companies, and city planners, all while trying to minimize disruption in one of Africa's busiest urban centers. But despite the complexity, progress continues steadily, with visible changes appearing year by year. New roads lined with smart lighting, new districts emerging with coordinated urban layouts, and data centers forming the digital core of the city's new systems. What makes the Addis Ababa City Corridor project stand out isn't just its scale, but its symbolism. Ethiopia is positioning itself as a regional leader in technology and infrastructure, and the capital city is its proving ground. The project represents a shift from reactive urban growth to proactive, technology-driven design, an attempt to future-proof a city that's expected to keep growing for decades to come. And when it's complete, Addis Ababa could stand as one of the first truly smart cities on the African continent, built not just to handle its population, but to evolve intelligently alongside it. There's a highway in Japan that cuts straight through Tokyo Bay, but it doesn't just go over the water like most bridges. It actually dives under it. This is the Tokyo Bay Aqua Line, a massive piece of infrastructure that connects the city of Kawasaki on the western shore to Kisarazu on the eastern side. And it does it with a combination of bridge, tunnel, and an artificial island sitting right in the middle of the bay. Before it opened, getting from one side of Tokyo Bay to the other meant driving all the way around it, which could take more than 90 minutes depending on traffic. The Aqua Line slashed that time down to about 30 minutes. That alone would be enough to justify a major investment. But to make it work, engineers had to go beyond traditional design and figure out how to cross one of the most heavily used bodies of water in Japan without disrupting the massive shipping traffic moving in and out of Tokyo's ports. So they split the structure in two. The first section, starting from Kawasaki, is a 4.4 kilometer bridge stretching out over the bay. Then, halfway across, the bridge ends on a man-made island called Umihotaru, which acts as both a rest stop and a transition point. From there, the road drops into a 9.6 kilometer tunnel that continues under the seabed and eventually surfaces in Kisarazu. That tunnel was one of the most technically demanding parts of the whole project. Digging a tunnel under the sea is never easy, but this one had to be done in soft soil while also accounting for seismic activity and saltwater corrosion. They used shield tunneling machines to dig through the seabed, installing thick concrete linings behind them as they went. The tunnel also had to be equipped with constant ventilation, pressure monitoring, and emergency access routes, since even a minor failure under that much water could be catastrophic. The artificial island, Umihotaru, wasn't just a place to change from bridge to tunnel. It was essential to the construction process. It provided a base for equipment, a place for workers to operate from, and eventually became a fully operational service area for travelers, complete with food, shops, and viewing platforms. It's also a venting station for the tunnel beneath. The Aqua Line officially opened in 1997 after roughly a decade of construction. And even though it was expensive to build and initially struggled with high tolls limiting traffic, it's become a vital connection for the region. It's also a showcase of Japan's ability to deliver complex infrastructure in harsh conditions, with multiple engineering disciplines, civil, marine, transportation, all working together to make it happen. Projects like this don't just solve traffic problems, they prove what's possible when design and execution come together at scale. But the real question is, would your country ever build something this ambitious? Or is this level of risk and investment unique to places like Japan? Let's hear what you think in the comments. By the middle of the decade, one of North Texas's earliest soccer-specific stadiums is undergoing a comprehensive reconstruction that places it firmly among Dallas area megaprojects active in 2026. The new Toyota Stadium redevelopment in Frisco represents a multi-year modernization effort focused on structural capacity, revenue generation, climate mitigation, and long-term event flexibility rather than a simple renovation. Toyota Stadium originally opened in 2005, designed for a different era of Major League Soccer and a much smaller regional population. The redevelopment project restructures the existing stadium rather than replacing it, allowing FC Dallas to continue operations while construction advances in carefully sequenced phases. By 2026, the project is deep into its most technically demanding stage, with heavy construction occurring throughout the seating bowl, concourses, and building systems. Construction work during 2026 concentrates on major structural modifications. Entire sections of the lower bowl are being demolished and rebuilt to adjust rake angles, improve sightlines, and support additional vertical loads from new premium levels above. New concrete pours and steel framing are installed in phases to maintain stadium stability, while adjacent areas remain operational. This year also includes reinforcement of existing foundations to meet updated building codes and support heavier roof and canopy systems. One of the most visible construction efforts in 2026 is the installation of expanded canopy structures. These roof elements are designed to significantly increase shaded seating, addressing long-standing heat exposure issues. The canopy construction involves large-span steel trusses, integrated lighting mounts, and future-ready broadcast attachment points. Installation is staged section by section to allow partial stadium use during the soccer season. Premium seating and hospitality spaces dominate interior construction in 2026. New club lounges, lodge boxes, and suites are being built into previously underutilized stadium volume. This requires extensive mechanical and electrical upgrades, including new air handling units, upgraded power distribution rooms, and expanded data infrastructure. Plumbing systems are also being replaced or rerouted to serve higher capacity food and beverage operations. Concourse reconstruction is another major focus in 2026. Existing concourses are being widened, regraded, and reconfigured to improve circulation and accessibility. Vertical transportation systems, including elevators and stairs, are being added or relocated to comply with modern accessibility standards. These changes require careful coordination between demolition crews, concrete teams, and utility installers to avoid service disruptions. Technology infrastructure work accelerates during 2026. Crews are installing new fiber optic backbones, wireless access systems, and security networks throughout the stadium. Dedicated broadcast rooms and control spaces are under construction to support national and international television requirements. These systems are designed to accommodate future tournaments and non-soccer events without additional major retrofits. Outside the Stadium Bowl, 2026 construction includes the redevelopment of surrounding plazas and entry zones. Pedestrian circulation is being improved through expanded hardscape areas, upgraded lighting, and reworked security screening layouts. These exterior improvements are engineered to support higher peak attendance and year-round events, not just match days. Sustainability measures are integrated into the 2026 construction scope. Lighting systems are being converted to high-efficiency LED fixtures. Water infrastructure is upgraded with low-flow systems, and stormwater management improvements are installed to reduce runoff during heavy rain events. Older materials removed during demolition are being recycled or reused where feasible to reduce construction waste. From a timeline perspective, 2026 represents the midpoint of the redevelopment. Structural and exterior envelope work dominates early and mid-year, while interior build-outs continue into late 2026 and beyond. Some premium areas and upgraded seating sections are expected to open in phases as construction completes, allowing incremental increases in stadium functionality. Major construction activity is scheduled to continue through 2027, with final interior finishes, technology commissioning, and operational testing extending into late 2027. Full project completion is expected between late 2027 and 2028, depending on seasonal construction constraints and event scheduling. The phased delivery approach ensures continuous stadium use while transitioning the facility to its final configuration. North of Dallas, in one of the fastest growing urban corridors in Texas, the Fields Entertainment District in Frisco is emerging as a large-scale, mixed-use mega project that is actively under construction in 2026. The development is positioned within the broader Fields master-planned community, a multi-thousand-acre site designed to accommodate long-term population growth, corporate expansion, and regional tourism demand. The Fields Entertainment District is planned as a dense concentration of sports, hospitality, retail, dining, and public space, anchored by major destination users rather than traditional suburban commercial formats. Unlike single-purpose developments, the district is structured to operate continuously, supporting large events, daily foot traffic, and future transit-oriented growth. Its scale and phasing place it among the most consequential Dallas area megaprojects progressing through construction in 2026. By 2026, horizontal infrastructure work is largely complete, allowing vertical construction to dominate activity across the district. Roadways, utility corridors, stormwater systems, and site grading were established in earlier phases, enabling simultaneous construction of multiple buildings. In 2026, cranes, concrete crews, and steel framing operations are active across entertainment venues, hotels, parking structures, and retail blocks. One of the primary construction focuses in 2026 is vertical development of large format entertainment and event buildings. These structures require long-span steel framing, high-capacity foundations, and extensive back-of-house infrastructure. Construction includes structural steel erection, roof decking, and exterior enclosure systems designed to accommodate high occupant loads and advanced audiovisual systems. These buildings are engineered to support concerts, live events, and large public gatherings. Hospitality construction accelerates during 2026. Multiple hotel components within the district are rising simultaneously, with reinforced concrete and steel structures progressing floor by floor. Interior build-outs begin on lower levels as upper floors continue structural work. Mechanical and plumbing systems are sized for high turnover and large conference or event-driven occupancy patterns, reflecting the district's destination-oriented role. Retail and dining blocks are also under active construction in 2026. These buildings are designed with flexible floor plates to allow tenant customization while maintaining consistent architectural standards across the district. Construction includes storefront framing, exterior finishes, service corridors, and shared utility infrastructure. Emphasis is placed on pedestrian connectivity with covered walkways, plazas, and integrated outdoor seating areas built alongside vertical elements. Parking infrastructure represents a significant portion of 2026 construction activity. Multi-level parking garages are being built to serve entertainment venues, hotels, and retail uses. These structures require rapid cycle concrete construction and are designed with future adaptability in mind, allowing potential conversion or integration with autonomous or shared mobility systems later in the project's life cycle. Public realm construction expands significantly in 2026. Central gathering spaces, landscape plazas, and pedestrian spines are being formed as adjacent buildings reach enclosure stages. Hardscape installation, lighting systems, wayfinding infrastructure, and drainage features are constructed concurrently to ensure these spaces are operational as individual components of the district open. These areas are engineered to manage large crowd movements during peak events. Utility and systems integration is a major technical focus in 2026. Electrical substations, district-wide communications networks, and centralized security systems are being installed to support high-demand uses. Fiber networks are integrated throughout the district to support digital signage, ticketing systems, and event broadcasting. These systems are coordinated across multiple buildings to function as a unified operational environment. Well before the first match of the 2026 FIFA World Cup is played in North Texas, downtown Dallas is undergoing a coordinated series of infrastructure and venue upgrades that collectively form one of the region's most complex mega-project efforts active during 2026. Rather than a single construction site, the World Cup preparations consist of multiple overlapping projects focused on transportation, public space, security, mobility, and event operations, many of which reach peak construction or final delivery during 2026.
On the eastern edge of San Francisco, where rusted cranes once loomed over a forgotten stretch of shipyard, the Pier 70 redevelopment is one of the city's most ambitious megaprojects currently under construction in 2026. This historic industrial zone, nestled between the Dogpatch neighborhood and the bay, is being transformed into a vibrant waterfront community, one that blends housing, jobs, public parks, and restored heritage structures into a single cohesive district. The construction underway this year marks the most active phase of the project to date, with key milestones approaching as the site charges toward completion in the early 2030s. As of 2026, multiple parcels across Pier 70 are under simultaneous construction. Residential towers are climbing skyward, with the first phase of housing expected to be completed by 2027. These buildings will deliver nearly 1,100 homes in their initial stage, 25% of which are reserved as affordable housing. Construction crews are also working on major infrastructure upgrades across the site, including new streets, transit corridors, pedestrian paths, and shoreline protections to guard against sea level rise. The heart of the megaproject is its connection to the past. Pier 70's redevelopment in 2026 doesn't erase its history, it builds on it. Several historic buildings are being restored and repurposed. These include old machine shops and steel foundries that once supported the shipbuilding industry. In 2026, many of these structures are undergoing seismic retrofitting and interior renovations to be converted into arts venues, retail hubs, and office space for design and tech firms. The goal is to preserve the gritty industrial character of the site while making it usable and vibrant for a 21st century city. Public space is a major focus of the construction effort in 2026. Over 9 acres of parks and waterfront access points are being built across the site. The highlight will be the large central green, an expansive park framed by restored industrial sheds and framed by views of the bay. As of this year, grading, drainage, and landscaping are underway, with full park openings projected for 2028. These open spaces are being built to double as climate infrastructure, designed to absorb stormwater, manage heat, and protect the site from flooding. In addition to housing and public amenities, the commercial component of Pier 70 is actively rising. Office buildings tailored to life sciences, technology, and creative industries are under construction now, with tenants expected to begin moving in by 2027-2028. These buildings are designed with flexibility in mind, featuring adaptive floor plans, outdoor terraces, and energy-efficient systems. Construction in 2026 is focused on delivering the first phase of these workspaces, helping to establish Pier 70 as an employment hub linked directly to the city's evolving economic base. The location is also a key asset. In 2026, construction crews are coordinating with transit agencies to enhance connections between Pier 70 and the rest of the city. Muni lines, bike lanes, and pedestrian links to the nearby Dogpatch neighborhood are all part of the ongoing infrastructure work. There's also future planning underway to accommodate ferry service, which would further connect the development to the regional transit network. When fully completed in the early 2030s, the Pier 70 redevelopment will deliver over 2,000 housing units, 2 million square feet of office and commercial space, 9 acres of parks, and over 300,000 square feet of retail, cultural, and community uses. But in 2026, it's the construction activity that defines the project. Foundation work, steel framing, historic preservation, and shoreline transformation all unfolding simultaneously.
In the quiet countryside of southern France, surrounded by pine forests and rolling hills, there's a construction site unlike any other on Earth. It's not another dam or bridge or skyscraper. It's a machine built to recreate the power of the sun. This is ITER, the International Thermonuclear Experimental Reactor, and it represents one of the most ambitious scientific collaborations in human history. The goal here is nothing short of mastering nuclear fusion, the same reaction that fuels stars, and turning it into a practical source of energy for our planet. The concept sounds simple in theory, but has pushed the limits of engineering for decades. Fusion happens when two light atomic nuclei, usually forms of hydrogen called deuterium and tritium, collide at extremely high temperatures and fuse into helium, releasing enormous amounts of energy. The problem is that replicating those conditions on Earth means creating and controlling plasma that's hotter than the core of the sun, about 150 million degrees Celsius, and keeping it stable long enough to extract useful power from it. That's where ITER comes in. At the heart of the project is the tokamak, a donut-shaped reactor designed to contain the plasma using magnetic fields so powerful they could lift aircraft carriers. The machine itself is a masterpiece of precision. Its vacuum vessel weighs over 5,000 tons. Its superconducting magnets are cooled to near absolute zero, and every component must align with millimeter accuracy, despite being the size of a small building. The idea is that when the system is fully operational, the reactor will produce 10 times more energy than it consumes, something no fusion experiment has ever achieved before. What makes ITER truly remarkable is how global it is. It's being built through a partnership of 35 nations, including the European Union, China, the United States, Russia, Japan, India, and South Korea. Each partner contributes different components, from cryogenic systems to magnet coils to diagnostic sensors, and all of them have to fit together perfectly when assembled in France. Coordinating that kind of international supply chain is an engineering feat in itself, with massive pieces of hardware shipped across oceans, and transported by custom-built convoys that crawl through rural roads to reach the site. The scale of the infrastructure around the tokamak is equally astonishing. There's a massive cryoplant to cool the magnets, a system of vacuum pumps, cooling water loops, radio frequency heating systems, and an entire electrical network dedicated to feeding the experiment's colossal appetite for power. When ITER begins its first plasma runs, it will consume more electricity than a medium-sized city, though the aim is to prove that fusion can eventually produce far more energy than it uses. Yet the challenge isn't just technical, it's also philosophical. Fusion has been called the energy of the future for over half a century, and ITER's success or failure could finally determine whether that future is real. If it works, it could open the door to commercial reactors that generate clean, virtually limitless energy from seawater, with no carbon emissions and almost no radioactive waste. But for now, ITER remains an experiment, a monument to human cooperation and scientific persistence, standing quietly in Provence as thousands of engineers and scientists work to capture the power of the stars here on Earth. Sometimes a project comes along that just doesn't make sense, at least not until you see it, drive across it, and realize what it actually represents. The Hong Kong-Zhuhai-Macau Bridge is exactly that kind of project. It's not just a bridge, it's not just a tunnel. It's a 55-kilometer long leap of engineering that crosses one of the busiest shipping lanes in the world, links three massive cities that used to feel far apart, and proves that China is willing to push infrastructure to extremes in ways few countries ever dare. To understand why it matters, you've got to look at the geography first. The Pearl River Delta is one of the most densely populated and economically powerful regions on the planet, with Hong Kong on one side, Macau on another, and Zhuhai anchoring the mainland. But even though these places look close on a map, getting between them used to take hours. Ferries, detours, congested roads. It was all slow, fragmented, and inefficient. So China decided to stitch the region together with a single mega link, one that could handle freight, commuters, and cross-border travel in one seamless shot. But building it wasn't simple. For starters, the bridge had to survive typhoons, earthquakes, and heavy marine traffic, all while standing in soft, muddy seabed that doesn't exactly love supporting massive pylons. Then there's the tunnel, because at one stretch, the bridge actually disappears beneath the water for over 6 kilometers to make way for ships. That required building 2 artificial islands out in the open sea, just so the road could dip down, dive under the shipping channel, and then rise back up again without interfering with maritime traffic. And that's where the engineering really hits you. The immersed tube tunnel, made up of huge prefabricated sections, was floated out, sunk into a trench, and sealed together underwater. Each section had to fit perfectly, with zero room for leaks or shifts. Above that, the bridge sections were hoisted into place using massive cranes, forming a ribbon of concrete and steel that curves and bends like a sculpture across the sea. When it finally opened in 2018, after nearly a decade of construction, the bridge cut travel time between these cities from several hours down to about 30 minutes. But beyond the time savings, it's a symbol. A signal that the Greater Bay Area is no longer just a loose collection of cities. It's becoming a single, interconnected mega region, one where borders blur and infrastructure drives integration. Of course, it hasn't been without controversy. The cost was enormous, the environmental impact was debated, and questions about who benefits the most continue to come up. But if you're talking about sheer ambition, about looking at a map and deciding to redraw it with concrete and cable, then the Hong Kong-Zhuhai-Macau Bridge stands in a league of its own. South of Dallas's central business district, the K. Bailey Hutchison Convention Center is undergoing a comprehensive expansion and reconstruction that places it among the most consequential megaprojects under construction in the city in 2026. The project is not a simple addition to the existing facility. but a phased redevelopment designed to modernize one of the largest convention centers in the region while maintaining event operations throughout construction. The expansion replaces large portions of the aging convention center with new structures that significantly increase usable exhibition space, improve circulation, and align the facility with current national convention standards. The redevelopment is also closely tied to downtown Dallas's broader urban strategy, including connectivity to surrounding districts and preparation for major international events. By 2026, the project is in its most intensive construction phase. Demolition of outdated exhibition halls and support spaces has largely been completed, allowing new structural work to dominate the site. Crews are actively engaged in deep foundation construction, including drilled piers and mat foundations designed to support long-span exhibit halls and multi-level meeting facilities. These foundations are engineered to accommodate heavy floor loads associated with large conventions and trade shows. Superstructure construction accelerates throughout 2026. Steel framing for expansive exhibit halls is erected using long-span trusses that minimize interior columns and maximize flexible floor space. Concrete cores housing vertical circulation, mechanical shafts, and life safety systems rise concurrently. The sequencing of this work is carefully planned to allow portions of the existing convention center to remain operational while new sections are built adjacent to them. Exterior enclosure becomes a major focus during 2026. Crews install curtain wall systems, precast panels, and roofing assemblies as structural work reaches completion in phases. These systems are designed for durability, energy efficiency, and acoustic performance, reducing operational costs and improving the experience for both exhibitors and visitors. Interior construction advances rapidly in 2026 across completed structural zones. Mechanical, electrical, and plumbing systems are installed to support modern convention requirements, including high-capacity power distribution, advanced HVAC systems, and extensive data infrastructure. These systems are designed to accommodate simultaneous large events with high technology demands, such as trade shows requiring heavy electrical loads and extensive connectivity. Circulation and access improvements are a critical component of the 2026 construction scope. New concourses, meeting room clusters, and pre-function spaces are being built to improve wayfinding and reduce congestion. Vertical transportation systems, including escalators and elevators, are installed to efficiently move large crowds between exhibit levels and meeting spaces. These improvements address long-standing operational limitations of the original facility. Site and infrastructure work continues alongside vertical construction in 2026. Roadway realignments, service access improvements, and utility upgrades are underway to support increased event traffic and logistics operations. Stormwater management systems are being upgraded to meet current standards and reduce flood risk in a historically vulnerable area of downtown. From a scheduling perspective, 2026 represents a midpoint to late middle stage of the overall redevelopment timeline. Major structural elements of the new expansion are expected to be completed during this period, with enclosure and interior build-outs extending into subsequent years. Phased openings allow new sections of the convention center to come online while construction continues elsewhere on the site.
In 2026, right in the heart of San Francisco's Soma district, the 5M project stands as one of the city's most active megaprojects under construction. This mixed-use development is bringing new energy and density to the blocks surrounding Mission, Fifth, and Howard Streets. Long a patchwork of surface lots and low-rise structures, designed to create a live work-play ecosystem in the center of downtown. The 5M project is pushing forward this year with the final phases of its build-out, aiming for full completion by 2027. The core of the project is a multi-building, multi-acre redevelopment that includes housing, office space, community facilities, and public plazas. As of 2026, the residential component is nearing its final stages, with interiors being completed, amenity spaces outfitted, and streetscape work wrapping up. One of the tallest residential towers in the project, now visibly finished on the exterior, is expected to open its doors by early 2027, offering a mix of market rate and affordable units, over 300 in total. The office and commercial buildings that anchor the project are also active hubs of construction. Fit-outs are progressing in multiple towers, preparing space for tech, nonprofit, and creative sector tenants. In 2026, these buildings are expected to start welcoming their first occupants by the end of the year, with full occupancy likely achieved in 2027. It's part of a broader shift in the area, as Soma continues to re-establish itself not just as a tech district, but as a vibrant, mixed-use downtown core. What sets 5M apart in the landscape of San Francisco's 2026 megaprojects is its emphasis on integration with the community. More than just a real estate development, the project was designed to create active public space and cultural infrastructure. At the center of the site, the 5M Park, currently under construction, is being landscaped with flexible gathering areas, art installations, and play zones for families. This green space is scheduled to open alongside the residential buildings in mid-2027 and is expected to become a crucial urban amenity for residents, workers, and visitors alike. This year, the construction crews are focused not only on completing vertical structures, but also on activating the ground plane. Sidewalks are being widened, bike infrastructure is going in, and retail storefronts are being prepped for future cafes, shops, and local businesses. The aim in 2026 is to finish creating a neighborhood that doesn't shut down after office hours, a place where people live, work, eat, and gather 7 days a week. One of the most significant elements under construction now is the dedicated nonprofit office hub and arts space, which will house multiple local organizations and creative initiatives. This facility is central to the 5M vision, supporting equity, inclusion, and community-based growth in a rapidly evolving part of the city. Completion is on track for late 2026, with programming expected to launch shortly after. From a development standpoint, the 5M project is compact compared to some of the sprawling waterfront megaprojects elsewhere in San Francisco. But in 2026, it punches far above its weight in terms of impact. Located just blocks from Powell Street BART and Muni lines, its density and transit connectivity make it a model of sustainable urban development, and its blend of housing, employment, and civic use is already influencing how other central city projects are being designed.
Tucked away in the mountains of Guizhou province in southwestern China, there's a gorge so deep and narrow that sunlight barely reaches the river at the bottom for most of the day. And spanning this massive cut in the earth, high above the mist and cliffs, engineers are building something that almost defies belief: the Huajiang Grand Canyon Bridge. When complete, it will stand among the highest bridges ever built on the planet. A structure so tall that if you dropped a skyscraper from the deck, it would fall for seconds before touching the valley floor. The numbers behind it are staggering. The bridge deck will rise over 600 meters above the river, which means it's taller than most observation towers and higher than the top floor of the Shanghai Tower. To put that in perspective, imagine stacking 2 Eiffel Towers end to end. That's roughly the drop from the roadway to the canyon below. This kind of height doesn't just make for dramatic photos, it turns every stage of construction into a feat of courage and precision. Workers spend their days suspended hundreds of meters in the air, guiding steel cables, assembling segments, and balancing heavy machinery on platforms that hang in the clouds. The Huajiang Grand Canyon Bridge is part of a new expressway that will connect cities across Guizhou, one of China's most mountainous provinces. Historically, this region was isolated by its terrain, deep valleys, twisting ridges, and karst formations that make road building incredibly difficult. The bridge is designed to close one of the biggest gaps, cutting travel times from hours to minutes, and linking communities that once felt worlds apart. In a province known for its poverty and difficult logistics, projects like this aren't just about transport, they're about access, trade, and opportunity. Structurally, it's a suspension bridge, chosen because it's one of the few designs that can handle both the span and the height of the canyon. The main span stretches more than 1 kilometer across, supported by enormous cables that anchor into the mountains on each side. The anchorages alone are buried deep in concrete and rock, absorbing the colossal tension forces that hold the deck steady. Every component must withstand fierce winds, extreme temperature shifts, and the constant pull of gravity across an open void. Even the construction of the towers is an achievement, with cranes and scaffolding perched on cliffs that would make most people's legs shake just looking down. What makes the Huajiang project even more impressive is how it reflects China's relentless drive to conquer geography with infrastructure. Guizhou has become a global showcase for bridge engineering, home to more of the world's highest bridges than any other region. Each one seems to push the limits a bit further. Higher decks, longer spans, faster timelines. The Huajiang Bridge is simply the next leap in that sequence, proving that there's almost no terrain too challenging to cross. When it finally opens to traffic, drivers will glide across a stretch of road that looks like it's floating between mountains, with clouds drifting below and the canyon yawning far beneath. It's one of those places where engineering and nature meet in a way that's both awe-inspiring and humbling, a reminder of what human ingenuity can achieve when the landscape dares us to go higher. There's a stretch of highway in southern France where drivers suddenly find themselves suspended in the sky, so high in fact that they're actually above the clouds. That's not poetic exaggeration, that's the Millau Viaduct, one of the tallest bridges in the world, and a megaproject that pushed both structural design and aesthetic ambition to new heights, literally. The story of the Millau Viaduct starts not with engineering, but with frustration. For years, travelers moving through the Tarn Valley, especially in the summer, were stuck in endless traffic jams around the town of Millau. The region's rugged terrain made road construction difficult, and the narrow valley routes couldn't handle the growing number of vehicles. A bypass was needed, and the only logical way to make it work was to go over the valley instead of around it. That's when the idea of a viaduct, a long bridge-like structure crossing the entire gorge, began to take shape. But this wasn't going to be any ordinary bridge. The span needed to be long enough to cross the entire Tarn River Valley in a single, clean sweep, and high enough to avoid disrupting the delicate environment below. That meant building a multi-span cable-stayed bridge more than 2.5 kilometers long, with a road deck floating nearly 270 meters above the river at its highest point. That's taller than the Eiffel Tower. And it's not just tall, the structure is elegant, sleek, and razor-thin, blending into the landscape with minimal visual weight despite its colossal size. The design was a collaboration between French engineer Michel Villelogeux and British architect Norman Foster. Villelogeux handled the structural genius, while Foster added the graceful visual language. Together, they created a design that looks light but performs under massive loads. The bridge has 7 pylons, each supporting a section of the deck with cables arranged in a fan pattern. The tallest pylon reaches 343 meters from the base to the tip, making it the tallest bridge support in the world. Building it required extraordinary precision. The deck was constructed in segments and launched outward from each pylon using a method called incremental launching. That meant carefully pushing out steel segments over thin, temporary supports, balancing the structure as it stretched across empty space. Crews worked at incredible heights, often exposed to winds and weather, with every component measured to the millimeter. The alignment had to be perfect. Any misstep would throw the entire bridge off balance. The Millau Viaduct opened to traffic in 2004, and the transformation was immediate. The days of traffic crawling through Millau disappeared, and the journey across the valley became something drivers actually looked forward to. You don't just cross this bridge, you experience it. There's a moment, especially early in the morning, when the valley below is still filled with mist, where the road seems to float above the clouds. And for a few minutes, you're not just driving, you're soaring. But beyond the visual drama, the Millau Viaduct is a textbook example of how a mega project can solve a real-world problem while also becoming a piece of national pride. It's functional, efficient, and yet built with a sense of beauty that makes it far more than just infrastructure. Set slightly apart from the historic core of downtown Dallas, the Bank of America Tower at Parkside represents one of the most prominent vertical mega projects under construction in the Dallas region in 2026. Rising within the Park District near Clyde Warren Park, the tower is positioned as a next-generation commercial office building designed to consolidate major corporate operations while redefining the northern edge of the central business district. The project consists of a high-rise office tower with a large floor plate, advanced building systems, and integrated public realm improvements. It is designed to accommodate a single major anchor tenant while also supporting multi-tenant flexibility. The structure replaces older, lower-density development, reflecting a shift toward taller, more efficient office buildings in Dallas's core employment zones. By 2026, the Bank of America Tower at Parkside is firmly in its vertical construction phase. Structural framing dominates activity throughout the year, with reinforced concrete cores and post-tensioned floor slabs rising steadily above street level. Tower cranes remain on site through most of 2026 to support formwork, rebar placement, and concrete pours as the building progresses floor by floor. Facade installation becomes a major focus during 2026. Curtain wall systems, consisting of high-performance glass and metal panels, are installed from the lower levels upward as the structure tops out. This work is carefully sequenced with interior construction to allow mechanical and electrical rough-ins to follow closely behind the enclosure of each completed floor. The facade is engineered for solar performance, glare reduction, and long-term energy efficiency. Interior construction accelerates significantly during 2026. Mechanical, electrical, and plumbing systems are installed across multiple levels simultaneously. This includes high-capacity HVAC systems designed for dense office occupancy, advanced air filtration, and smart building controls. Electrical infrastructure includes redundant power distribution and backup systems consistent with large financial and corporate tenants. Elevator installation is another critical task, underway in 2026. High-speed elevator shafts are completed within the concrete core, followed by cab installation, guide rails, and control systems. These systems are designed to minimize wait times while serving a tall structure with large floor plates and high daily occupancy. Ground-level construction remains active throughout 2026 as well. The tower integrates structured parking, loading docks, and secure service access beneath and adjacent to the building. Streetscape improvements, including widened sidewalks, landscaping, and pedestrian connections to nearby parks and transit routes, are constructed alongside vertical progress. These elements are coordinated with city infrastructure upgrades to minimize disruption in a dense urban environment. Life safety systems are installed and tested in phases during 2026. Fireproofing, sprinkler systems, smoke control, and emergency power infrastructure are integrated as each floor reaches substantial completion. These systems must be commissioned incrementally to support ongoing construction above occupied or enclosed levels. From a scheduling perspective, 2026 represents the midpoint to late middle phase of the project timeline. Structural topping out is expected either during or shortly after 2026, depending on sequencing and weather conditions. Once the structure is complete, focus shifts more heavily toward interior finishes, tenant build-outs, and systems commissioning. Major construction activity continues into 2027, with interior finishes, lobby construction, exterior plaza completion, and final facade detailing extending well beyond the structural phase. Testing and commissioning of building systems, including elevators, HVAC, and security systems, are expected to continue through late 2027.
Buried beneath the surface of San Francisco's downtown in 2026 is one of the city's most consequential megaprojects under construction, the Portal, also known as the Downtown Rail Extension. This massive underground infrastructure project is finally being realized after decades of delays, aiming to connect Caltrain and eventually California's high-speed rail directly to the Salesforce Transit Center. As of this year, excavation work is ramping up, tunneling contracts are active, and the city is fully committed to completing the extension by the early 2030s. In 2026, the Portal is a hive of subterranean activity. Tunnel boring preparations are in progress, utility relocation is underway, and major downtown streets are experiencing stage disruptions as crews create access points for the underground guideways. It's one of the most complex transportation builds in the Bay Area, requiring coordination beneath some of the densest blocks in the city. Once complete, this megaproject will deliver a seamless rail connection from the peninsula and Central Valley straight into the financial core of San Francisco. The project involves building approximately 1.3 miles of new track, mostly underground, to link the existing Caltrain line near 4th and King with the Salesforce Transit Center. In 2026, the staging areas at both ends of the project are fully operational. Pile driving, shoring walls, and structural reinforcements are all happening in real time as the city begins to carve out the physical corridor that will carry thousands of passengers daily. Construction in and around Townsend, 2nd Street, and the south of Market area is active and accelerating, with visible impacts above ground and substantial progress being made below it. The Portal isn't just a rail project, it's a regional unlock. In 2026, Caltrain still terminates at 4th and King, about a mile short of downtown. That last mile has long been the missing link in Bay Area transit. By closing that gap, this project will plug regional rail directly into San Francisco's business core, reducing car dependency and reshaping how people move across the region. When complete, the Portal will allow Caltrain riders to disembark in the heart of the city and will set the stage for future high-speed rail service to run directly from Los Angeles to downtown San Francisco, without transfers. The current timeline targets a completion date in the early 2030s, with most heavy construction expected to occur between 2026 and 2030. In the context of San Francisco's other megaprojects under construction right now, the Portal stands out for its invisibility. Most of the work is happening underground, but the scale of its impact will rival that of any tower or waterfront redevelopment. Cost is high, risk is real, and coordination is intense. Crews are navigating under live utilities, major foundations, and transit lines. Every foot of tunnel requires precision, and every stage of construction must account for seismic resilience, waterproofing, and integration with existing BART and MUNI infrastructure. In 2026, engineering teams are deep into geotechnical work and soil stabilization, preparing for the eventual tunnel boring operations that will begin in earnest in 2027. Jordan Downs wasn't built to last, but it lasted. What began in the 1940s as temporary war worker housing in the heart of Watts evolved into one of Los Angeles's most recognized public housing projects. For decades, it stood as a symbol of neglect, of disinvestment, of the city's fractured promises. Now it's at the center of one of the largest and most complex urban redevelopments ever attempted in Southern California. This is the Jordan Downs redevelopment, a multi-phase billion-dollar megaproject that's rebuilding an entire neighborhood from the ground up. We're not talking about a simple renovation. This is full-scale urban reconstruction, replacing over 700 aging public housing units with a mixed-income community of more than 1,400 new homes, complete with parks, retail corridors, a new street grid, and state-of-the-art infrastructure. And all of it is happening while people still live there. That reality, redeveloping a live-in community without displacement, is what makes this project such a massive logistical and engineering challenge. Everything had to be phased. Crews couldn't just level the site and start fresh. Instead, new housing blocks were constructed in stages on available land, allowing families to relocate within the community as old units came down. That required intense coordination, not just in construction, but in utilities, access roads, and safety systems, all while keeping the neighborhood functioning. Before any new buildings could rise, the land itself had to be re-engineered. Jordan Downs sits on a former industrial site, contaminated from decades of adjacent manufacturing. That meant full environmental remediation, soil testing, removal of hazardous material, groundwater management, and installation of protective barriers. Engineers excavated tens of thousands of cubic yards of earth, replacing contaminated soil with engineered fill, compacted and monitored for stability. Next came infrastructure. The original Jordan Downs layout was a relic of mid-century planning. Isolated blocks with limited connectivity and almost no integration into the surrounding street grid. To fix that, the project involved installing an entirely new road network, complete with sidewalks, bike lanes, storm drains, and underground utilities. A major extension of Century Boulevard now runs through the site, connecting it to the broader Watts area and giving the community a direct arterial link to the rest of the city. Structurally, the new buildings are designed for both density and resilience. Wood frame over concrete podiums dominate the design, balancing cost efficiency with seismic durability. Each structure is engineered with fire suppression systems, earthquake-resistant framing, and energy-efficient insulation to meet California's Title 24 building codes. Sustainability was also baked in. Solar panels, drought-tolerant landscaping, and stormwater capture systems are integrated across the site. And unlike the original layout, the new Jordan Downs is being built with mixed-use development at its core. A central retail village is part of the plan, complete with grocery stores, cafes, and community-serving businesses. That required additional engineering for load-bearing slabs, commercial-grade ventilation, and enhanced utility access to support food service and retail operations. The project also includes new parkland, recreational facilities, and space for schools and job training centers, all of which had to be laid out on what was once a closed, fenced-off grid.
In the vast emptiness of northwestern Saudi Arabia, where desert and mountains stretch endlessly under the sun, a line of glass and steel is being drawn across the landscape, a city unlike any that has ever been built before. It's called The Line, and it forms the central vision of NEOM, a futuristic megaproject meant to redefine what urban living can be in the 21st century. The idea sounds almost impossible at first, a city that isn't sprawling outward, but extending straight for hundreds of kilometers, only 200 meters wide, yet home to millions of people. But that's exactly the scale of ambition Saudi Arabia is pursuing, nothing less than the reinvention of civilization itself. The concept behind the line begins with simplicity. Instead of spreading a city outward in all directions, it compresses everything into a single linear corridor that runs through desert valleys and over coastal plains. The two mirrored walls of the city rise more than 400 meters, enclosing a narrow interior where people will live, work, and travel vertically rather than horizontally. The structure is designed to function as a continuous vertical metropolis, where everything, from housing and offices to schools, parks, and public transit, is stacked efficiently inside a climate-controlled environment. At its core, the line is meant to operate without cars, roads, or traditional streets. Instead, it relies on a high-speed underground transport system that can move people from end to end in minutes. The idea is that every daily need, groceries, healthcare, education, recreation, should be within a 5-minute walk. By eliminating cars and long commutes, the designers aim to create a city where time is reclaimed for people, where nature and urban life coexist without one overwhelming the other. Sustainability sits at the center of the entire plan. The line is being built to run entirely on renewable energy, primarily from solar and wind power, and its compact footprint minimizes land use and environmental impact. The vertical design allows the surrounding desert and mountains to remain untouched, preserving natural ecosystems while housing millions of people in a fraction of the space that a normal city would require. The structure's mirrored facade isn't just aesthetic. It reflects sunlight to reduce heat absorption and helps control the city's internal temperature. Engineering something of this magnitude pushes the boundaries of what's physically possible. The foundation requires precision construction over uneven terrain, and the structural demands of building two continuous walls, hundreds of meters high, across such distances are immense. The integration of transportation systems, data networks, energy grids, and vertical living spaces has to function seamlessly for the vision to work. Every part of the city will be monitored and managed through AI-driven systems, adjusting lighting, temperature, and logistics dynamically to optimize efficiency and comfort. The line also represents a broader idea about the future of Saudi Arabia. It's not just a mega project, it's a statement of national transformation. It reflects the country's drive to diversify beyond oil, to attract technology, investment, and global talent, and to present itself as a center of innovation. For the government, the line is both an economic experiment and a symbol of ambition, projecting the image of a nation willing to take risks to shape the next century. Whether it succeeds or not, the line is already changing the conversation about what cities can be. It's forcing engineers, architects, and planners around the world to imagine new forms of living, new ways of organizing society, and new relationships between humans and the environment. In the middle of the desert, a city that runs in a straight line may seem improbable, but that's precisely the point. It's a bet on imagination and on the belief that the future doesn't have to look anything like the past. In a country that's already known for doing things on a grand scale, Lusail City might be the most ambitious vision of all. It's not just another district or a new development on the edge of Doha. This is an entirely new city, built from the sand up, with skyscrapers, marinas, stadiums, and entire neighborhoods that didn't exist just a few years ago. And what's even more striking is that it was all designed to be ready in time for one of the biggest global events Qatar has ever hosted, the 2022 FIFA World Cup. Now, when most countries host the World Cup, they upgrade a few stadiums, maybe improve some roads, and polish the existing cities. But Qatar did something different. They decided to build a city, And not just any city, a futuristic, master-planned urban center that could one day rival major global capitals. That's Lusai. At the heart of it all is Lusai Stadium, a golden, bowl-shaped structure that became the centerpiece of the tournament. It held the opening and closing ceremonies, and it's where the world watched the final match play out in front of a roaring crowd. But Lusai wasn't built just for football. The stadium was only one piece of a sprawling urban puzzle that includes business districts, residential towers, tech hubs, shopping centers, and an entire waterfront lined with parks, walkways, and yachts. It's the kind of place designed not only to impress visitors, but to lay the groundwork for a post-oil economy. Something sustainable, modern, and globally connected. What makes Lusai stand out is how fast it all came together. Less than 2 decades ago, this was just empty desert. No roads, no buildings, just a bold vision and a whole lot of heat. And in that short time, workers and engineers transformed the landscape with underground tunnels, smart grid infrastructure, and cutting-edge cooling systems that keep the city livable even in Qatar's brutal summer. There's a light rail system that zips through the streets, fully integrated into the larger metro network, and nearly everything is designed with energy efficiency in mind. But as impressive as it is, Lusai also raises questions. Will people move there? Will the city thrive after the World Cup spotlight fades? Because building a city is one thing, filling it with life is something else entirely. Right now, Lusai still feels new, still in the process of becoming what it was meant to be. Office towers are waiting for tenants, apartments are waiting for families, and time will tell if it turns into the vibrant, buzzing metropolis that planners envisioned, or if it remains a symbol of ambition more than reality. Still, as a feat of engineering and construction, Lusai City is remarkable. It shows what's possible when you have the resources, the will, and a clear goal on the horizon.
The Mission Rock project is one of San Francisco's headline megaprojects under active construction in 2026. Sitting directly south of Oracle Park, on what was once a windswept sea of asphalt and overflow parking lots, this 28-acre waterfront site is being turned into a dense, walkable neighborhood that combines housing, parks, offices, and retail in one of the most high-profile real estate efforts in the city. In 2026, the project is deep in Phase 1 construction. Several major buildings have already topped out, with exterior work wrapping up and interior build-outs ongoing. Full completion of this phase is expected by late 2027. When finished, it will include nearly 1,200 new residential units, over 400 of which are permanently affordable, along with 8 acres of new public space and over 200,000 square feet of office and retail space. This megaproject isn't just reshaping a site, it's helping to redefine the southern edge of San Francisco's downtown. New streets and pedestrian promenades are already being laid out, stitched together by green infrastructure and open-air plazas designed to absorb stormwater and resist sea level rise. The waterfront park, known as China Basin Park, is being built in tandem with the buildings around it. Crews in 2026 are currently sculpting the park's shoreline and planting native vegetation, with major portions set to open by 2028. Mission Rock is a public-private partnership between the San Francisco Giants and the Port of San Francisco, and the construction in 2026 reflects a long-term vision to extend the city's core outward along the waterfront. Designed as a high-density, low-emissions community, every new structure is being built to LEED Gold or higher standards. Solar panels, all-electric systems, and smart energy grids are standard here, not just features. One of the project's architectural landmarks now under construction is the Canyon, a massive mixed-use building that blends market-rate apartments with carved terraces and retail space. In 2026, the Canyon's facade is nearly complete, and interior work is progressing toward a mid-2027 delivery. Nearby, a life sciences tower being built for the biotech sector is rising quickly, with tenants expected to begin occupancy by late 2028. What makes Mission Rock such a key part of San Francisco's 2026 megaproject landscape is its fusion of uses and its central location. Unlike isolated developments on the city's edges, this project plugs directly into the transit network and urban fabric. It's within walking distance of downtown, BART, Caltrain, and multiple Muni lines. Its completion will not only provide urgently needed housing, it will expand the city's job base and public amenities in a place long dominated by underused land. As of 2026, the construction site is a hive of activity. Steel framing, glazing, mechanical installation, and hardscape development are all occurring simultaneously across multiple parcels. Each building is being developed by a different architectural team, resulting in a diversity of forms and styles that break from the monolithic look of some other megaprojects. This is intentional. Mission Rock is designed to feel like a neighborhood, not a master plan. The entire project is expected to wrap up in multiple phases through the early 2030s, with new parcels starting construction as others finish. By the time it's fully built out, Mission Rock will include 8 acres of parks, up to 1.4 million square feet of commercial space, and space for thousands of new residents.